First of all, we should talk a little bit about what Wireshark is. Wireshark is used for packet capture and analysis, and by that I mean that Wireshark will actually grab all of the network communications as they pass across your network interface. This means not only the messages that are destined for you, which your network card will commonly filter for, but anything that passes across your network interface can be grabbed by Wireshark. The real advantage to using a tool like Wireshark is because you can't change data that is on the wire, meaning once it hits the transmission medium, either the Ethernet cable or the air if you're using wireless, it's too late to do anything about it. Applications can lie sometimes, or maybe you don't get really reliable logs. Once you are looking at the network transmissions, you are looking at what is really going on within your network. Wireshark is actually great. It's been around for a long time. It used to be called Ethereal. It does a lot of translations for you. So it performs the binary to English translation. It does deep protocol decoding, so you can actually see what's really going on without having to do a lot of what does this hexadecimal digit mean or what does this particular header mean. You can also get a lot of statistics and graphs with Wireshark to get a bigger picture view of what's going on in your network. Speaking of hands-on, what we're going to be working through is really a lot of hands-on work. We're not going to be looking at slides, the first couple of slides notwithstanding here. We're going to be looking at real-life captures so we can actually get a real sense of what the protocols really look like and how they operate. So welcome again, and I really hope you enjoy the series of videos that you will be watching, and I really hope you learn a lot and get a lot of deep insight into how Wireshark works and what it can do for you in terms of understanding networking and improving your troubleshooting capabilities in your network or system administration or whatever job it is that you're doing that has to do with your network. So you may be wondering what it is we're going to be covering over these few dozen lessons around Wireshark. We've got a topic list here, so kind of at a broad, big picture view, we're going to be looking at capturing and viewing packets using Wireshark. We're going to be looking at how to perform analysis using the capabilities that Wireshark has. We're going to be looking at statistics that Wireshark can generate. These statistics will be really helpful as you're doing your analysis and trying to troubleshoot using Wireshark. We're going to be looking at some voice over IP or telephony capabilities. And finally, we're going to be looking at some advanced topics, primarily around the command line and using some of the command line functionality that Wireshark installs. At a more detailed view, we're going to be looking at capture filters, display filters, generating graphs, doing time analysis, using the dissectors that are built into Wireshark in order to actually break apart the different protocols so that you can understand more clearly in plain English, more or less, what's actually going on rather than just looking at raw hexadecimal or binary. We'll also be looking at generating statistics from Wireshark, and the statistics will be really helpful in determining how much traffic is passing from one end to the other, who's generating the most traffic. This can be really helpful as you are doing troubleshooting and analysis on your network, as you're really using Wireshark to understand what's going on. We're going to be using a couple of different capture sources. First of all, I'm just going to be capturing packets on my local network wherever possible, and where I don't have quite as much capability locally. So, for example, some of the telephony things which are more complicated to get set up and perform captures around, we're going to be using the pcapper.net website in order to download some PCAP files that we're going to be doing some analysis from. The pcapper.net website is actually a really good source of just packet captures that you can use in order to get a better understanding of the different protocols. The packet captures are broken out by protocol on that website, so if you've got a particular protocol that you want to see in action, you can actually use pcapper.net in order to download a packet capture that demonstrates that protocol, and then you can really get a clear understanding of what it's doing. Well, the first thing that we need to do before we can actually start capturing packets is that we need to acquire a copy of Wireshark. So I'm going to go to wireshark.org. Once we are at the website, of course, there's some features here. We can get acquainted with it. You can get help. You can join the project in order to develop it. Remember, Wireshark is an open source project, so you can actually get the source code to Wireshark, and if you're really interested, you can see how it actually works. What I'm going to do is I'm going to just go to download, and of course I could get the source code if I wanted to. I'm going to use the development release in this particular case only because it has a newer interface design to it and there are some additional features. I could certainly go back to the stable release. If you've got Windows, you can install 64 or 32-bit. And of course, we've got OS X here. There's also the ability to install under Linux. If you've got Linux, you can certainly install most of the major distributions, if not all of the major distributions, actually have Wireshark either installed by default or just something that you can install very quickly with whatever the package manager happens to be. In my case, I'm going to go with an OS X installation package here, so we're going to download that, and once that's downloaded, I can install it, and once I've got it installed, the interface is pretty much going to be the interface regardless of what operating system that we're using. I'm going to be using Mac OS X because that happens to be the operating system that I commonly use. And I'm going to install Wireshark inside Mac OS X. If you want, you could get the Windows installer for either 64 or 32-bit. And again, if you've got Linux, you can very easily install Wireshark on your Linux distribution if it isn't already installed. Then that's something that you should probably check before you go trying to install it. Just save yourself a little bit of time. Just see whether it's in the menu system, or if you're on a command line, just see if you've got Wireshark there. Once you've got it installed, then we can move forward with what we're going to be doing with Wireshark. Since we're talking about capturing network packets, we should really talk about network architecture. I want to take a look at two particular network designs, and these are really simplistic, but they're a pretty common way of looking at the way your network may be put together. On the right-hand side is really the most common way today, and that's where you have a switch that is connecting all of your systems. This could even be like a wireless access point, which behaves in a way that is similar to a switch. In a switched network environment, as you can see on the right-hand side, we have computer A or laptop A trying to communicate with laptop B. So we've got laptop A sending in a message to the switch in order to get to laptop B, and then the switch directs the traffic only to laptop B, which is kind of the way you would expect it to be. Except that until we had the capability to build switches in a cost-effective manner, what we were left with was a hub. If I were to go from laptop A here and I wanted to send a message to laptop B, what the hub would do would be to send it out every interface that it had. Not only would B get it, but C would get it as well, and frankly, everybody else who was connected to the hub. In this case, I've got a very limited network diagram with only 3 systems. If I were to have a larger network, what would happen would be the hub would send it absolutely everywhere. So you can see that a switched environment is better in the sense that only the recipient gets the traffic that is meant to go to that particular recipient. It's not just sent everywhere on the network. So what does this mean when we're talking about packet captures? If I am capturing packets on the network, there's a good chance that I want to see more than just the messages that are destined for me. I probably want to see everything on the network. So there's a couple of things that I can do. What I can do is I can take this switch and I can set a port span so that, for example, C gets all of the traffic that is coming into the switch. That's one way of doing it. I could also do something that we're going to talk about next, which is just spoofing all of the addresses so that everything on the network actually comes to me regardless. And then I just take the switch out of the situation. I may not actually have the right to make the changes to the switch that we're talking about here, because setting up a port span so that all traffic goes to you is something that requires A, access to the switch, and B, administrative access to the switch. I would need to be a particular type of user, a network administrator, network engineer, somebody like that, in order to go in and get that configured, or I would have to know that person. Of course, ideally, I would know that person anyway, because I really need permissions in order to do this type of activity, this packet capture. The other problem that we've got is lower end switches like home switches don't really have the capability to do things like port spanning. And so what we end up having to do is something like spoofing that we will get into coming up in a subsequent lesson. Now, the problem of getting traffic to you if you're in a switched environment and you don't have the ability to make alterations to the switch. Well, one of the ways is we could use a program called Ettercap, and Ettercap does something called ARP spoofing. What ARP spoofing is a way to pretend that you are another device. All devices everywhere, if they have any sort of communication network capability, have a media access control address or a MAC address. That MAC address is sometimes called a physical address because it's actually bound to the physical interface. We are going to actually pretend that we are other devices by sending out ARP responses where no ARP request has been made. So we're going to say we are every device on the network. I'm going to set my interface to do some unified sniffing here. Now, if I go to man in the middle, I can say ARP poisoning. And actually, before I do that, I need to set host. So we're going to scan for hosts. And then we're going to look at the host list. Now, from here, what I can do is I can select a number of hosts and I can add them to my targets. One of the things I want to do is I want to make sure that my gateway is in a different target pool than the hosts that I actually want to do some ARP spoofing for. The reason for that is because we actually want to make sure that we get both ends of the communication stream. So if a host is actually communicating with a website, we want to make sure that we get the response. And that response is going to come from the gateway, which in my case is actually at this address here. So if I were to add some hosts to my host list, then what I could do would be to go and say ARP poison. And once I start up the man in the middle attack and do some ARP poisoning, what I'm going to be doing is sending out a lot of ARP requests that are going to get the traffic to come to me. Once it has come to me on my network interface, then of course I could use something like Wireshark to capture it. Now, another utility that I could actually use is one called ARP Spoof. ARP Spoof comes with a small utility package called dsniff. And dsniff has been around for a really long time. It was created by a guy by the name of Doug Song, and it was used to actually parse network communications to extract email messages and various other file types. In order for dsniff to work, though, it needed to be able to do some ARP spoofing. What I'm going to do here is I could specify my target, and I want to make sure that I specify my host, so I could use ARP spoof to do the same thing that Ettercap does, just a very simple command line version of that. So if I do ARP spoofing, I can get a lot of network communication to come to me. Of course, if I'm only going to be looking at network communications that I am originating and come back to me anyway, then I really don't need to do any of this. You don't have to get involved in ARP spoofing if you're looking at either just your own traffic, in other words, traffic that is coming to you, or broadcast traffic or communications that are coming out from your interface. Then you don't have to worry about any of this. This is just for the case where you are on a network and you have permission to do some packet captures, but you don't have the ability to set up a port span on your switch. So, for example, you may have an unmanaged switch that can't actually do port spanning. You just have a very simple switch, so you need to do something like ARP spoofing in order to get all of the traffic coming to you. Well, now we've got ourselves a copy of Wireshark and we figured out how to get packets to us. Now let's talk about how we can actually start a packet capture. First of all, let's take a look at Wireshark itself so that you can see the toolbar across the top. One of the easiest things to do is just click this button right here and it will just start capturing packets. But there are other ways to start capturing packets as well. So you can see down here in the main window the list of interfaces. And again, this is version 2.0. Version 1.x looks slightly different than this, but you could still see the list of interfaces that were available on the system. The nice thing about this new interface is you can actually see very quickly here which interfaces actually have traffic on them. We've got the loopback interface here, which is just local only traffic. So that's only network messages that are going from this system to this system on a special loopback interface. The other one that is actually seeing network traffic right now is EN0. So that's my Ethernet interface. And you can see that we're getting traffic because we're getting graph changes here over time. Now, if we get to the very end, it looks like there's not an awful lot happening, although we did see some spikes periodically here. In order to just start a capture, as I said, I could certainly go up here and start a capture there. There are menus. If you are running on a Windows machine, you'll get a menu. On a Mac system, there's the menu across the top that you could go to and start a packet capture. What I'm going to do is I just double clicked on the interface and you can see that I'm immediately getting packets that are being captured here. Let me just stop this and I can do another thing here where I'm just going to show you start capturing packets. If I click this, first of all, it's going to ask me whether I want to save the packets that I have captured already. And I'm going to say continue without saving. So again, if I go back to the main screen, then I can just select the interface. I can double click it, start capturing packets that way, or I can just click the little icon up here that says start capturing packets. So this is a little shark fin, actually, because of course the name of the program is Wireshark. I can click the shark fin and just start capturing packets. And just to familiarize yourself with the interface here, up top in this top frame, what we have is the list of frames. Now, we're talking about packet captures, and a packet is actually a group of data. It's a particular way of thinking about the data, but it's only at one layer of the network stack. What we're actually getting here is frames, and what I might have is multiple frames going into a packet. The reason that we're looking at frames is because that's the way that it comes in across our network interface when we're talking about the messages that are going across the network interface. These are all frames, and then again, they could be aggregated up into packets at the IP layer. Datagrams, for example, might be at UDP. And so we could also have segments if we're talking about TCP. So you may hear different ways of referring to the collection of data or the data units. In this particular case, and I'm just going to stop this here. If I click the big red box, I can stop capturing packets. Each one of these is actually called a frame, and you'll see here we've got our frame right there. we've got the way of capturing packets, and then you can kind of see the Wireshark interface. We'll be digging deeper into the Wireshark interface as we go. This is just kind of a brief overview of what we are looking at here. Now I'm back to the primary window that you would get when you start Wireshark up. The reason for that is because I want to actually look at the capture options that we have. There are settings that I could go into in order to set different parameters around how we are capturing packets. Let me just go into my settings here. So in my case, in this particular interface, I'm going to go to capture options. Again, with the older Wireshark, you're going to find capture options in different places. Ultimately, what you're looking for is capture options. So you might find that in the menu, for example. You might find it in the toolbar here, just like this. Or, as I said, in the older interface, you might actually find the capture options down along with the interfaces themselves. And that's not the case here with this current version of Wireshark. So I'm going to go into capture options. And immediately what we get is a set of options that are available. And again, we get the traffic graph here. If you look under the traffic column, you'll get the traffic graph for the interfaces that we have. So I've got my list of interfaces, and I can pop this open and I can see the addresses that are associated with this particular interface. So I have my IPv6 address, and then I have my IPv4 address as well. So I can go into manage options, and then I can either show or not show the different interfaces. So for example, if I didn't want to show the bridge 0 interface, I could uncheck that. And I can look at pipes if I had some pipes, and if I had the ability to do remote interfaces. And you can see this particular version of Wireshark does not support remote interfaces. They don't happen to have any anyway, but I could manage my interfaces there. The other thing that I can do is I can check my output options. I can say I want to output to the PCAP next generation format, or more common is just the PCAP format. There's a wider range of programs that support just the PCAP and don't necessarily support the PCAP NG output format. And then over here, we've got options. So I could resolve network names. And the network name would be, if I've got an IP address, it would resolve the IP address for me. So I could go to network names. So I'm not just looking at IP addresses, I'm actually looking at actual host names. And I can also resolve the transport names. What this means is that I would get the actual name of the port. So, for example, instead of just seeing 22 under a port identifier, what I would see would be SSH if it were a TCP frame that we were looking at. So I can go to resolve network names, I can resolve transport names. Of course, that's going to slow me down because it's going to have to look up the network names and transport names as it goes. So if you want to go faster, you can just uncheck those, and then you can look them up later or go into display when you've actually got a capture, and then you can actually look up the names at that point. So depending on how quick you want your responses showing up here, you can either check or uncheck those. And of course, I could also not resolve MAC addresses. What that means is if I resolve the MAC address, you'll actually get the name of the vendor that's associated with the particular network interface. So those are the different options that you have when you are capturing packets or capturing frames and packets through Wireshark. Now, we've done some capturing of some frames over an Ethernet interface, and commonly you'll be doing a lot of packet captures over Ethernet interfaces. It is the most common layer 2 protocol that you would use. So we've got an Ethernet interface right here. That's my wired connection. What you're going to have, though, is a Wi-Fi connection sometimes as well. Now, with a Wi-Fi connection, we can certainly capture the Ethernet headers because we do use Ethernet over Wi-Fi. So our layer 2 headers are going to be Ethernet in order to make use of the media access control addresses or the MAC addresses. And so we've got that header, but the other header that you want to look at is the radio header. So with Wi-Fi, we're sending out radio signals between our local systems and the access point. Or if you're using an ad hoc network, you might just send messages from you to another system in your ad hoc network. Now, by default, we would have the ability to listen to the radio headers disabled. That's this monitor mode right here. You can see that we've got disabled set on our Wi-Fi interface. The link layer header we're setting at Ethernet at the moment, and of course promiscuous mode is enabled on all of the interfaces. That's so that we can capture every piece of traffic that goes across our interface, whether it's actually destined for us or not. What I want to do is I want to set monitor mode to be enabled, and then in this particular case, what I'm going to do is I'm going to set the link layer header to per packet information, because I actually want to get the radio traffic and I don't want it to try to determine that that's an Ethernet header. I'm going to click start here, and then we're going to immediately start seeing a lot of traffic that is going by. And you can see we've got our 802.11 header. We've got 802.11 radio information right here, and you can start to see beacon frames. If we scroll down a little bit, we should see some beaconing that's going on from the various access points that are available within some reasonable proximity of me. So what we're seeing here is we're seeing a lot of radio packets. So this is the really low-level connection between our system and the wireless access point. And you'll see all sorts of data that you would otherwise just not be able to see. So we've got an association response here where a system is trying to associate to an access point. And we've got a number of other frames as we scroll down that you can see. These are just 802.11 frames, and 802.11 is Wi-Fi. It's the kind of overarching set of protocols that determine wireless networking. Again, in order to capture traffic that is Wi-Fi, I'm just going to close this here, and then we're going to go back and take a look at the options again. They are fairly simple, but you want to make sure that you are doing this in order to get the Wi-Fi information. You want to make sure that monitor mode is enabled, and if you've got this option here as well, you may want to set your link layer header to per packet information. Once you start capturing frames using Wireshark, you run the risk of being overwhelmed with the amount of data that you're going to get. If you've got an idea of what it is you're trying to accomplish, what you might want to do is set a capture filter. Right here, we've got the ability to set a capture filter. One thing I can do is I can specify a protocol, for example, or I could specify a host. Let's say I wanted to do my particular host, so I would say 172.30.42.13. So I could specify that kind of information in order to set a capture filter. So let me choose an interface here, and then we're going to say 172.30.42.13 is going to be my capture filter. You'll see once it's got a valid capture filter, it actually turns green, where I was getting the pink or the red before when I was typing in what would otherwise be a valid capture filter. The reason was I didn't have an interface set. So I've got my interface set here. So now all I've got to do, now that I've got my capture filter, is I can just start my capture. I could just double click here where it says Ethernet EN0, which is my Ethernet interface or my wired interface. The other thing I could do would be to go up and just click the shark fin here. All I would need to do would be to start generating some traffic. And now I'm generating traffic in another window. So you can see that we're actually capturing data here. I should never have any frame that I'm capturing that doesn't have 172.30.42.13 as either a source address or a destination address. With the host filter, what I'm doing is I'm saying that the IP address could either be in the source or the destination column. Before you start up a capture, then you might want to think about actually limiting the amount of traffic that you capture by setting a capture filter. Even if you don't set a capture filter, there are ways to limit or drill down to the specific set of information that you are looking for, even after you have started the capture. So don't fear if you've got a capture going and you really want to start drilling down and you didn't set a capture filter, not a big deal. But you can set a capture filter if you want, and you would do that. I'm just going to close this here, saying capture using this filter. So if I were to wipe this out, you can just start typing something and get a number of suggestions here. It will just pop them down. All I've got to do is start typing a letter, and it will offer me some suggestions of filters that I may want to use. Wireshark will actually help you by providing you some information that may actually help you set a capture filter that you may want to use during your capture. I've got a packet capture going now, and the reason for that is I want to show you searching and sorting. I'm just going to stop the capture here at this point. It's going to make working with it a little bit easier so that things just aren't constantly scrolling up through. And I'm going to go all the way up to the top. Now, at the very bottom of the display here, you can see packets is 555, and we're displaying 555 out of that. So I've got 555 packets or frames that we have captured, and I want to actually be able to locate information a little bit more easily. So the first thing that I can do is I could actually sort by protocol. So if I click on the protocol column header here, it's going to sort by protocols. And you can actually see, if I do a little bit of scrolling on the right-hand side, you can actually see the colors show up. And the colors, if you start to get used to them, you begin to recognize what the different colors are for. I happen to know that HTTP is green. And so if I were to start scrolling, I would need to get down to this level here to get to HTTP, which is where I see the green frames. So above that is blue, that's DNS. You can see that we've got a number of ARP frames as well. You can see that we can sort based on protocol. You can sort based on source. We've got a mixture of IPv4 and IPv6 frames. I'm just going to pull that out a little bit more so you can see the different addresses that we've got here. When I sort here, I'm going to get my IPv4 frames at the top, and then probably my IPv6 frames are going to be at the bottom. And then at the very bottom, because we are going by source and destination, and it's ordering on what we call ASCII order, meaning that it's looking at the characters. So the numeric characters come first, and then we get the alphabetic characters. And what we've got here is the vendor ID for this particular media access control address. So that happens to be Apple, and this is the Eris group, and then we've got Samsung down here. So these are all ARP messages, and we don't have an IP address. All we've got is the MAC address, so that's what we're looking for here. If I want to go back to the original order, all I've got to do is click on number, and then of course I can order reverse or forward on any of these different column headers here. I can sort in either direction. So the other thing that I can do, if I go to edit and then find, what I'm going to get is a whole new section here where I can search the packet list, I can search the packet details, which is maybe what I want to do. And then I could do either narrow or wide characters. A narrow character is only 8 bits long. That's a typical ASCII character. Unicode would be a multi-byte character set. So here's a wide character set that is 16 bits wide. I'm going to search narrow and wide. I can select string or hex value, depending on what it is that I am looking for. What I want to do here is I just want to search for notify. Notify should show up in some messages that look like HTTP messages. So if I search for notify, There's the first one right there. And you can see in the info field on the right-hand side, it says notify. And what I can do is pop open the HTTP headers here, and then I've got notify there. That's where I found notify. You can search and sort here, and we can use those different techniques in order to get more efficient about how you are locating information that you have captured. Now that we've got a packet capture in front of us and we've actually started to look a little bit more deeply into it, let's actually look even deeper and figure out what we've got here. As I've mentioned before, Wireshark is actually really good at pulling the data apart for you and presenting it in a way so that it's really easy to understand. So what we've got here is you can think a little bit here of the different networking models. So you've got the OSI model, and you've got the ARPA model as well, or the TCP/IP architecture. What we've got starting at the very bottom here is you can think of this as the first layer. What this says is we've got a frame. It's number 174. We've got 419 bytes on the wire, and that translates to 3,352 bits. And 419 bytes were actually captured on that first interface. Moving up, we actually have the Ethernet header here. This is the layer 2 header where we've got the source and destination MAC address. We've actually got the type of the packet we are looking at here. This refers to the next header. So typically what you would get would be an indication in one header to tell the receiving device what is going to be in the next header so it can figure out how to pull it apart. So this tells us that we've got an IPv4 message, so we are going to be looking at an IP header in our next set of data here. So we're up to layer 3 at this point, where we have the source and destination IP address, and then we've got the various IP headers here as well. So we've got the IP identification field, which allows us to identify messages that have been broken up into fragments. And if I've got a message that has been fragmented in some way, this IP ID field here will identify all of the different frames that are associated with that complete packet. In this particular case, we're looking at the flags. This one says don't fragment, so we don't actually want the message here to be broken up into fragments. So, of course, fragment offset means that this is the very first fragment, not surprisingly, since it wasn't supposed to be fragmented to begin with. We've got the time to live header, and then we've got, again, the protocol, which tells us what the next layer is going to be. In this case, it's going to be UDP. And then we can just skip down to the UDP header, which is a very simple header. It has the source port and the destination port, as well as the length. The source port is 35,880. The destination port is port 1900. And so that actually is associated with universal plug and play. That's actually what this message is all about. And then, of course, we've got the length indicating how long this particular message actually is. We've got the ability here to very quickly and easily pull apart the different headers. And of course, this is the application header here where it's the hypertext transfer protocol. And you've got all of the information that has been provided here associated with this particular HTTP notify request. We've got the HTTP header at the application layer, UDP, Internet Protocol, and then, of course, we've got our Ethernet header at layer 2. So you can select any one of these here, and you can break it apart very easily so that you can identify what type of message it actually is. This one, for example, is DHCP version 6. So we've got a UDP header right here, and then we've got the DHCP message. We've got the ability to select any one of these messages and have Wireshark help us by pulling the message apart very easily in a way that is easy to read in a human readable fashion. If you want to read it as though you were a machine, of course you are free to do that. The message If I were to select it here, you could see it highlighted down below. This is the entire message, and you've got the hexadecimal on the left-hand side, and then the raw ASCII decode on the right-hand side. Neither of them are useful for most people. Therefore, it's much easier to just go up here and have Wireshark pull it apart and explain it to you. And that's how you would pull a frame apart in order to look at the individual headers and also the data from the application layer so that you can see what's going on. There are some things that we can do to manipulate the view. Now, what I'm going to do is I'm going to click on the View menu, and you can see the entire View menu, although you can't see the part that says View. What we can do here is we can make some changes in how we actually look at the information within Wireshark. One thing that I can do is I can remove the main toolbar, and that would mean that I would have to rely on the menu system that's available to us here. If I were to get rid of the main toolbar, you can see suddenly we've got more space for our information there. I can get rid of the filter toolbar if I don't want to have any ability to do display filters. I can add in a wireless toolbar, but wireless controls aren't supported in this particular version of Wireshark, so I'm just going to make that go away. I can get rid of the packet list. I can get rid of the packet details. This is the packet list right here. And then the next one down is the packet details. And then at the very bottom, we have the packet bytes. So I can change the time display format. I can zoom in if I need to see things a little bit better. I can change coloring rules, and then I could colorize conversations that would allow them to stand out more easily within the packet capture if I wanted to be able to do that. Of course, the other thing that I can do is I can start dragging columns around. So I could put my destination before my source. I can move the length all the way over here after the time. And then I can just move things anywhere that I actually want to here. I can grab any of the column headers that I want, and I'm going to just drop this back over here and then put it back kind of the way it was previously. So you can see that we've actually taken things a little bit out of order in the process of doing that. And again, all I've got to do to reorder it is click on the frame number column header, and then it will just reorder them for me. So we've got a number of different ways of changing the way Wireshark looks, and I'm actually going to restore the main toolbar, not because I necessarily need them, but sometimes it's nice to have easy and quick access to stop capturing packets and start capturing packets. I don't actually have to go up to the menu for that or get into keystrokes if that's what I want to do. So I'm just going to leave Wireshark kind of the way it is. This is really what I'm used to, so this is the way I prefer it. If you are not familiar with Wireshark, you may want to change things around and make them look a little bit different. Of course, the other thing that we've talked about before in terms of changing the column width so that you've got a little bit more space to look at some other details. For example, the info section here on the right-hand side, which is a real quick synopsis of what the frame is actually doing. You won't actually see that anywhere within the frame itself. This is Wireshark giving you a quick synopsis and pulling relevant information out of the frame details so that you can figure out which one you actually want to look at. So you may really want this to be much wider than some of the others. That's another thing you can do in terms of changing the view to something that's a little bit more amenable to you and the way that you work. Now I've got a packet capture here. What I want to do is I want to close this one, and I'm just going to continue without saving. The reason for that is I want a new capture, and I'm going to, while I'm talking here, just do a little bit of web browsing in a different window so that I've got some data here that we can actually look at. And what I want to do is I want a number of web connections that are available so that I can show you another concept here called streams. Anytime you start communicating with a particular website or a particular system, what you've started to do is you've started to create a conversation there, and that conversation actually can be tracked in a really useful way with Wireshark. And so what I've done here is I've just gone to a number of different websites while we've been talking about streams. And the reason for that is because I want a number of streams, which are really the conversations that are happening between the different hosts that we are communicating with. So right now I'm going to stop the capture. I think I've probably got enough at this point. I'm going to drag open the source and destination so you can see completely the source and destination here. We've got a number of TCP messages, and we're not really sure what these are, because what we've got is a TCP segment that is associated with a particular protocol data unit, or PDU. And one thing that we're actually missing here is we're missing source and destination port information, which would make things a little bit easier, other than I can see right here, this is port 60,125 to port 80. So it looks like we've got a number of communications going between 172.30.42.13, which is me, to 206.190.57.54. An IP address alone isn't really easy to track, although I can see pretty easily that we've got a number of these. I'm going to right-click on that particular frame, and then what I'm going to do is I'm going to say follow TCP stream. So when I've got a TCP communication going on, as I would in the case of going to a website, what I end up with is a stream, and that stream is the process of both ends communicating back and forth. So if I follow the TCP stream, what I end up with right here is all of the data that's associated with all of the frames that are part of that particular stream. So this is the entire communication at the HTTP level, so at the application layer, so you can very easily see what's happening. The red section here is the message that I sent off to the website that I'm communicating with, and in the blue is the response. And so what we end up having is a conversation going back and forth. I say something, and then the server replies. I say something else, the server replies again. And so it looks like what we've got here is probably an image. If we go back up to the GET request, we could actually see what the image was. It looks like it's not really clear what this actually is based on the URL, which is right there. And actually, when I highlighted that, you could see it changed the window behind, and it popped me straight into the frame that that particular section of this stream refers to. So if I were to select up here, the change would happen again. And then if I were to select up here, the change would happen one more time. So as I click through the conversation stream, Wireshark is actually pointing me at the frame in the packet capture that we are actually referring to here. I'm going to close this, and I want to show you something else. What happened was Wireshark automatically created a capture filter for me, and we'll get into more detail around capture filters a little bit later on, but the capture filter right here, TCP stream equals 520. The 520 is actually a stream designation that Wireshark has created because it has kept track of all of the conversations in the streams that have been going on through the packet capture. So this one happens to be stream 520. And then if I were to just click that X there, I would return to the entire packet capture. I could actually select another conversation, and I could do the same thing. So if I were to say follow TCP stream, I'm going to get a different TCP stream. But again, what I'm going to get is all of the data and none of the actual network headers. So I'm not going to get any of the IP headers, any of the TCP headers. I'm just going to get the data from the entire conversation that has been happening. This is really, really useful. So being able to extract streams and then get a complete decode of all of the data in one window is really useful, particularly as you're tracking web communications, because you may have a number of messages going back and forth through the conversation. To be able to see it all at once can be really helpful in really understanding who said what and when it happened and what the return was. In this lesson, we're going to be talking about dissecting packets or dissecting frames. With Wireshark, we have the ability to have Wireshark do a lot of the analysis for us in terms of pulling all of the bits and bytes apart to explain them in a really useful way. So we don't actually have to go down and say, well, what's that 33? What does that actually mean? Wireshark will do all of that for us. Now, sometimes Wireshark actually gets confused and doesn't always understand exactly what's happening. You can see in the protocol column here that Wireshark identifies a protocol that it is aware of. Now, if I were to go down and right-click on this here, what I could do is say decode as. So this is a TCP segment right here. And if I were to do a decode, what I get is a potential set of rules. If the TCP port is actually 80, the default is HTTP. It was basing this on the source port, which you can see down below here in the TCP section. The source port was 50,360, and so Wireshark said, oh, 50,360, well, I don't know what that is. If I say it's port 80, though, the default is actually HTTP. That's a particular decode that Wireshark is aware of. If I select over here under current, of course it says none because it didn't really find anything to do any decoding on. Now, if I were to scroll down, I could select something else, maybe, for example, SIP, because the session initiation protocol is actually based on HTTP. So I could say, no, that's actually SIP, or I could force it to do a decode as HTTP here, and then I click OK. And we haven't really changed anything because it didn't really find much of anything that looks like HTTP. This one down below, it did recognize as HTTP because, of course, there's a post message there. In this one, there's just a segment. It's not a complete packet. And so there's not enough really to go on here for Wireshark to say, oh, well, that's a complete HTTP message, and so it really couldn't do a decode for us. However, you may from time to time run into situations where Wireshark may not completely understand what it is that it's looking at, or if you have custom packets that you are looking at, what you can do is you could actually create a packet dissector of your own, and then you could do a decode. Of course, you can also set up additional rules if you wanted. So if you were to say IP protocol were equal to whatever this particular segment happened to show, then you could set up an additional rule here, which would allow Wireshark to determine what actually they're going to do the decoding as. You could set up a number of different rules here and tell Wireshark exactly how you want this particular segment to be decoded for you. So again, you're not having to do a lot of manual dissection and decoding to figure out what's actually happening with this particular segment or packet. Something that you may have noticed here as we've been looking at various packet captures is I'm looking at a lot of IP addresses. Now, some of these, like the 172.30.42.13, really aren't going to resolve to anything. Those are addresses on my local network. They are private addresses. And since I don't have any reverse DNS resolution set up on my local network for those addresses, they're not going to resolve to anything. 184.25.109.50, on the other hand, really should resolve to something. So you may have been wondering, as we've been sitting here staring at all of these numbers, why exactly that's not showing you something useful. Well, we can fix that. If I go to the view menu here, you can see the view menu. Now what I can do is I can toggle different resolutions here. These are name resolutions, so I could turn on resolve network addresses. The network addresses are the IP addresses, and once I turn on resolve network addresses, it goes through, does DNS lookups on all of those IP addresses that it can find, and then plugs in names. So we've got a1755.g.akamai.net now, rather than the previous IP address that was there. The other thing that we've got going on here is we've got numbers in for port names. I could also specify, if I go to the view menu again, I could resolve transport addresses. The transport layer is our layer 4, and that's TCP or UDP. So if I were to resolve transport addresses, you're going to fairly quickly see the 80s disappear in this column right here, and those should be replaced by HTTP. And sure enough, that's exactly what happened. We can do transport layer lookups and we can do network lookups. So the one thing that I will say about that is if you are doing this while you are capturing, then what you're going to be doing is generating a whole lot of DNS lookups as you are doing packet capture. So you're going to clutter your packet capture with the DNS resolution, trying to figure out what all of these IP addresses that are coming in are for. Because, of course, when you get a frame in or a packet in, what you're getting is the IP address because there's just a numerical field here. So if we look at this and we look at the source, actually, it's a chunk of hexadecimal digits here. And so we've actually got 4 bytes, and those are represented as hexadecimal numbers. There's really just numbers there. In order to make them human readable, that's where we turn name resolution on. So I'm actually going to quit this without saving, and I'm going to pop open Wireshark again, and we're going to take a look at what we could actually do right here as we are capturing for options. Here, we could actually resolve network names and we could resolve transport names, and we could check those as we are doing the packet captures, and it will fill those in automatically. Now, this may be one that you could do without generating additional frames because Wireshark is actually going to be aware of a lot of the common transport names. It's not going to have to actually look them up other than doing potentially a file lookup within Wireshark. Again, if you want to look up network names, that could generate some DNS traffic, which could clutter your packet capture. And then suddenly you're having to wade through all of these DNS lookups that you generated just in order to have network names. Better potentially in this case to do the resolution after the fact. Once you've got the packet capture, you can view and check the network addresses. It will resolve them at that point in time without actually adding additional frames or messages to your packet capture. Now, we've had a number of packet captures, and I'm actually going to start up a new one here. And I'm just going to click some links in a different window so that we've got some packets that we can actually do something with here. I've got a number of frames that we've actually captured. It looks like quite a number of them, and I think that's probably more than enough there. So let me just stop that. Seems like 19,000 packets is probably plenty. So we've got these packet captures, and we've been looking at them in real time, and I've been kind of closing and recapturing. The one thing that we haven't done to date is we haven't actually saved anything. What I want to do here is I want to show you saving. So I click the File menu, and I can go to Save. Now, I've got a number of options here. So there's a couple of things to be aware of. First of all, I can just save as a regular old PCAP. This is an old packet capture format. This is an older Wireshark format. It's going to work across a number of different programs and utilities. that's going to be a safe bet. Now, you can also store in the packet capture next generation, the Wireshark next generation format. That's the PCAP NG. You may have some additional challenges getting this particular file format to work with some tools. So this one is actually going to be the safest bet. Now, you could also save in some additional PCAP formats, but this one is actually going to probably be your safest. I'm not saying this is the one that you have to use all the time. If you are only using these packet captures for yourself, certainly the next generation packet capture format is the one that Wireshark is often trying to use more of. But if you're trying to be kind of useful across a variety of tools, then you probably want to just stick with the Wireshark TCP dump format. So now all I have to do is I have to plug in a file name, and I'm going to call it filename.pcap here. That's just a basic save. So the other thing that I could do would be to export frames or export packets. So I could export all packets. I could export selected packets. In this case, that would be just one. Something that you'll notice here is we could save captured and we could save displayed. If I go back here and I say HTTP, now I am showing just 1,386 packets out of 19,737. So suddenly, when I go to export specified packets, we've got the displayed and then we've got captured. So I could save all of the displayed, in this case, it says 7,782. So there's a bit of a discrepancy here in terms of the ones that are displayed between this number and the one in the status bar at the bottom. But it's going to export this number here, 7,782 packets. Or, of course, we could go back and select the captured packets here, and then we would get everything. So you can see we've got a couple of different ways of storing information. I could save the entire capture, or if I've got a good display filter here and I start actually weeding through all of the data, I could get rid of a bunch of frames that I really just don't care about, and then I'm only saving the frames or the packets that I really do care about. The export actually works well if you want to store some subset of the entire packet capture. Now, we've been looking at using Wireshark to perform captures, but Wireshark can also be used to open up captures that have been created from other sources. And frankly, there are a lot of different sources that use the PCAP format. One of them is a utility that you can find on a Mac OS system, which is what I'm running here. You can also find it on a Linux system, and there are variations of it that can be used on Windows system. So we're going to use TCP dump. Now, TCP dump allows me to perform various filtering activities. So I could do things like host 172.30.42.1, for example. So that's similar to the capture filters that we had looked at. But I've also got other things that I can do. If I want to store a file, what I can do is just say output.pcap, and that's going to write out all of the captured packets out to this file output.pcap. Now, the other thing that I need to do on this particular system is I need to specify the interface that I'm capturing on. In many cases, you're only going to have a single interface, so it's probably not going to matter much if you add this particular parameter or not. In my case, I've got several interfaces between a wired and a Wi-Fi, as well as some virtual interfaces for virtual machines and so forth. So in this case, I need to specify my interface is going to be EN0. That's really pretty much all I need to do. So I can just do TCP dump -w output.pcap and then say -i en0, and that's actually going to save my file out here, and I can actually go to a different window and generate some traffic that would be captured elsewhere. Now, the other thing that I need to be concerned with when I am doing a capture here is I may not be grabbing the entire packet. What I typically need to do is I might need to actually specify the packet length. We get 626 packets received by the filter here. I'm going to add a -n for my snap length, and I'm going to say 0. That's going to say just grab the entire packet. So I'm not going to care particularly what size it is. If I wanted to only look at headers, I could actually limit the capture size by only capturing, say, 40 or 60 bytes maybe, and then I might have all that I need in order to do whatever analysis I'm trying to do. In my case, what I want to do is I want to see the entire frame or the entire packet so that I can actually see all of the information that I've got. So, for example, if I want to identify problems with a web connection that I've got, I really need the entire frame so that I can look at the data portion as well. If I'm just capturing the headers, I'm not going to get the data portion. So I need to set my snap length using the -S0 so that I can actually get all of the packet rather than just some minimal amount that I might otherwise get. So now I can just say Control C and I can say ls output.pcap. I'm actually going to look at the whole thing. So I want to see the size of it. And sure enough, I've got my PCAP, and you can see it's about 160,000 bytes or so. And now that I've got this PCAP, of course, I could use Wireshark to open it and then do the analysis in Wireshark, because frankly, trying to look at the output of the PCAP here using TCP dump, even if we weren't writing it out. So for example, I could take the -W here and I could just do the capture here on the command line. Now I've got my data here. That's really kind of difficult to figure out what's going on. Certainly you can do it, particularly if you're skilled at this and you know what it is you're looking at, but it's quite a bit easier to do it within Wireshark. And so now that we've got our PCAP stored, we can actually go into Wireshark and we can do our analysis there. Okay, well, now we're back to Wireshark. And so from here, what we can do is we can just go open a file. We've got some capture files that we can take a look at here. So you can see right on the welcome page here, we've got a list of files that show up under open. I could just open up one of these, and that would be really easy. These are files that Wireshark is aware of, probably because we opened them up previously. And of course, I can also go to open a capture file here in the toolbar. And then, of course, if I click on the open in the toolbar, I've got a list of the files that are on my file system, and I can skim through the file system and locate the file that I actually want to open up. What I want to do here is I want to open up that file that we had created using TCP dump. So in this case, I'm going to go up to my file menu and then I'm going to say open. And in this case, it happens to be in my home directory. And so I'm just going to go to output.pcap. Now here, as I'm doing the open, I can have it do the name resolution, the transport resolution, and then the network name resolution while I am doing the open. So everything is right there. You can see that there are a large number of capture formats that we can actually open up using Wireshark. In this case, I'm just going to open up a PCAP file. Now, I have named it a PCAP file, and frankly, that's really only necessary for Windows systems where the file association would make a difference so that I could just open up the file in the Windows File Explorer. If it's named PCAP, Windows knows that that's associated with Wireshark. I could have frankly used .dump, which is another file extension that is fairly commonly used with packet captures. So I'm going to open up my output.pcap file. And of course, it took a second to open it up because it was doing all of the resolution for me for all of the IP addresses and all of the ports and all of the other name resolution that we actually had it do for us. I've just opened up my file. And now, of course, I can go and look through the packet capture. You can see this was the packet capture that we created using TCP dump. And it looks exactly like something that would have been created using Wireshark. And again, all I've got to do is I go to my open icon here on the toolbar, or I can go to the file menu and then I go to open. And again, file extensions are helpful for identifying what you've got in front of you. But frankly, the file extension is really mostly meaningful for Windows systems so that you can do the file association and then just go to the file, double click it, and have Windows automatically open it for you. Those are of less concern on other systems that don't do that same sort of file association. However, PCAP files or dump files are pretty common when we're talking about file extensions for packet capture utilities. Now, we've gone through creating packet captures, we've gone through opening them, we've gone through saving them. One thing that we may want to do is we may actually want to have Wireshark take care of automatically creating new files for us and doing a really long-term capture. I'm going to select my Ethernet interface, and I'm going to go to my settings, and then I'm going to go to output. In this case, I've got a choice of output format. I'm just capturing in PCAP form. I could do a capture to a permanent file if I wanted to do that. The other thing that I can do is I could create a new file automatically after, say, 4 megabytes. As soon as I hit 4 megabytes, I'm going to automatically create a new file. Now, the other thing that's really useful is a way to make sure that you're not filling up your disk, because as soon as I do this, create a new file automatically after 4 megabytes, I let Wireshark just run. Then what's going to happen is, as soon as I hit 4 megabytes, it's going to create a new file. I hit another 4 megabytes, I create another new file. Pretty quickly, if you let Wireshark run for a really long time, you're just filling up your disk with all of the network captures that Wireshark has grabbed. So there's one thing that we can do to alleviate that, which may be useful for you, and that's to use a ring buffer. Now, what a ring buffer is a set of files that we're going to loop through. So what I'm going to do is I'm going to automatically create new files, and then I'm going to go to the next file. So let's say we hit 4 megabytes here. We go to our second file. Hit another 4 megabytes. We go to our third file. Another 4 megabytes. Rather than creating a new file, what we do is we loop around back to the first file that we had created. So we've created a ring because we're constantly using the same files as we are doing these captures. So this is really useful because if you've got something that you're looking for and you want to have some kind of historical view, so let's say you've got a trigger, for example, you've got an intrusion detection system, but there's something that you think is happening before a particular event happens. What we can do here is set up a ring buffer. Let's actually bump this up a little bit. We're going to capture 4 files that have 10 megabytes each in them. That's a fair amount of traffic. It's not a huge amount, but it's a fair amount. And so the moment that our intrusion detection system pops off for us, we can go back to Wireshark, stop it, and then we've got that 40 megabytes that we can sift through that gives us a historic view into what happened leading up to that particular event. I don't want to fill up my disk, but I want kind of a historic view that goes back some number of minutes or maybe hours, and you kind of get an idea of how much traffic you're creating on your network to get an idea of how many files and how many megabytes that you need to capture. Then you can use this ring buffer feature. And again, you can kind of create as many files as you want and just kind of keep looping through those files in your ring buffer so that you've got that historic view into the network traffic that you can go back and refer to when something has happened. We're going to start looking at how you're going to use Wireshark to perform analysis. Analysis means that we're going to really pull packets apart, not only pulling packets apart individually, but also looking at the conversations and the interplay between frames and how everything comes together in terms of the entire conversation between systems, but also the entire network. So we're looking at the entire packet capture. What I'm going to do is I'm going to just pop open the output PCAP that we had previously grabbed, and I'm going to take a look at the expert analysis. So Wireshark actually does a lot of work for us. And one of the things that it does is it performs analysis on the entire set of frames that we have captured here. If I go down to the very bottom left, you can see that there's a little yellow circle. And if I mouse over that, there's actually a tooltip that pops up that says warning is the highest expert information level, and it pops up down below here where you can't see it. So let me just bring the window up so you can actually see the expert information, and we don't even have to worry about what the tooltip says or whether it's in the window that we're looking at or not. You can see that warning is actually the highest level that we've got, and that matches the yellow circle down below. There are 4 different colors that you might see indicating the severity. The highest color that you might see in the lower left-hand corner there is red. That indicates that there's a serious problem somewhere in the packet capture. Below that is warn, which is yellow, as we can see here. There's also a note, which you can see is a light blue or cyan. And then there's a chat, which in this case is a blue. And if you look at the documentation for Wireshark, they actually say it's gray, but here it looks more bluish to me. So we're going to go with blue. We've got a warning, and I can click on this, and it actually takes us directly to the frame in question. So this is frame 575, and it says it looks like this may be out of order. So what we've got here are some TCP analysis flags, and this is something that Wireshark has actually put in, and so we can look at what Wireshark is actually telling us. It says this is a suspected out-of-order segment. The frame is potentially out of order. This indicates that there may be something going on the network that we need to be concerned with. Wireshark actually flagged this particular frame as something that we should investigate a little bit more thoroughly. So I'm going to bring the expert information open again. And it looks like there's another one here that's an acknowledged segment that wasn't captured. Somewhere there was a segment that didn't actually get captured as part of everything that was here. So that's not necessarily anything to worry about. I could click it, and it's going to take us all the way down to frame 650, and we could look more closely at that. So I can also see all of the notes, and it looks like there are a number of frames that Wireshark believes may be a retransmission. Retransmissions are actually fairly common, depending on the network that you are working with. TCP actually handles retransmissions just as a matter of course. If one side doesn't receive a message within a particular time frame, so for example, if I'm sending a bunch of segments to another system and I don't get acknowledges back from that other system, I'm going to retransmit. So I need to get acknowledgments back on a fairly regular basis within some predefined parameter, which would be the window size. And if I don't get a message indicating an acknowledgement of the segments that I have sent or the packets that I have sent, then I need to retransmit to make sure that the other side got it. That's just part of the TCP protocol. It's completely expected. So that's why here what we've got are a number of notes. Because it's fairly common or certainly not unexpected, we can see retransmits showing up under notes rather than warnings or certainly under criticals. The other thing that you'll see when we're talking about retransmissions is that when we're doing a retransmit of a packet, sometimes it may get delayed, and I might actually resend a message that is still in transit and just hasn't arrived yet. What I might do is I might send it again, which might actually end up getting me a duplicate message. And what this says is we've got a duplicate acknowledge. That's also not completely unexpected. It happens sometimes. Packets get hung up in transmission, and then if you send another one, maybe it gets there faster. Then you end up potentially with duplicates. This is how you can allow Wireshark to really help you with doing some analysis on the packet capture that you've got so that you can see where there may be potential problems with the network communication that you have presented to Wireshark. So we've used the expert analysis, and now I want to show you a couple of different ways of locating errors within your packet capture. That doesn't mean errors in the capture, it means errors that Wireshark has identified in the frame. So there's nothing necessarily wrong with what has been captured, it just indicates there may be a problem with your network. So I'm going to open our filename.pcap that we have worked with previously. And again, I could go down and you can see we've got a red circle here. So we've got some errors, or at least one error. And if I pop open the expert information, you can see that we've got an error there. We can just kind of scroll down through here and we can use some visual inspection to make note of some places that we may want to look at. You can see that we've got a black line here. And what we've got is a port unreachable message. Somewhere we sent a message to a system that wasn't actually listening. So in this case, it looks like a DNS request, and we got a message back from that DNS request indicating that that port was actually not listening. We can continue scrolling around, and again, we've got another black line here, and then a couple more. Looks like some more port unreachable messages. And then if I keep scrolling, I will eventually come to a line that I probably want to pay a little bit more attention to. And that one is right here. If I click off this, you can see that it's a black line, which again kind of catches my attention. And then the text is in red. So what we've got here is a duplicate acknowledge, and you can see that it shows up in the information over here on the right-hand side. It says TCP dupe ACK 197 number 1. This is to an HTTP request, and you can see again, if you look at the information column on the far right here, it actually gives you a lot of information without even having to really open up the segment here or the packet that we've got in order to actually see anything more. I can really see a lot right in that information column. But of course, I can come down here and I've got the TCP open, and there's actually no HTTP here because this is just an acknowledged message. The TCP flag, if I click this open, it indicates that we've got the acknowledgement bit that is set. And then that's really just all there is to this one. There's a duplicate acknowledge, which again isn't necessarily something that we need to be particularly concerned about, but it is something that you may want to investigate. Again, I could use the expert analysis, but as I'm kind of flipping through here, I can click on here and it actually tells me in the information column, as well as just color-coded, where I've got a black line with red text. That kind of stands out to me a little bit and says, really, you should pay a little bit more attention to this message here. So I've got a number of duplicate acknowledges, and you will see this black line with the red text in other types of errors where you may want to pay a little bit more attention. So for example, if the checksums that the network stacks perform in order to make sure that what is sent is actually what's received, if the checksums don't match, you may actually get a black line with red text indicating that there's a checksum problem. And again, that may be something that you want to look at. So we've got a couple of different ways to fairly quickly identify errors. Certainly, we could use the expert information and allow Wireshark to tell us. Or as we're just kind of flipping through, you can see these black lines. And particularly black lines with red text are ones that you really want to pay a little bit of attention to, because those are problems with the communication that Wireshark has flagged from the packet capture. Now, we had looked at some capture filters earlier on, so we were only capturing exactly what we were looking for. There's another type of filter that I want to show you. So I've just started up a capture here, and I'm actually going to just do a little bit of browsing in another window as I'm capturing all of the traffic, just so I've got some interesting things to look up in our capture. So it's not just kind of a static, simple capture that we're looking at here. What I want to do is I want to create a display filter. Now, there are a lot of ways that we can apply display filters. There's a lot of capabilities with filters. I'm just going to show you some very simple ones just to demonstrate what display filters are and kind of how they work. And then you can certainly work with Wireshark, and it will really help you through building. Let's just say I want to do ip.addr, and you can see it's already popping up some suggestions for me. So if I want to do equals, I have to do equals equals, or I could also say EQ. The other way that Wireshark helps me out here is it actually turns the filter box here, or the edit box, a different color based on the status. Green means this is an okay filter. Of course, it's not going to do anything because I'm just looking at the IP address. I could now say equal 172.30.42. Let's say 13. As soon as I put the 13 in, you can see it changes to green. If I take it back to just 3 octets, Wireshark is aware that's not a legal address. All I have to do is hit enter. It is applied that filter. Now all we have are frames that have that IP address somewhere in them. You'll see here, for example, it shows up as the source here and the destination here. So I don't necessarily limit myself in terms of the address location. So it could be either the source or the destination. You'll see also that we've got displayed is 805 down here, and the total number of packets is still incrementing on the left. And of course, now my displayed is showing up. The displayed number indicates the number of frames that match this particular display filter. If I wanted to be very specific here, I could say ip.source equals 172.30.42.13. And now all I've got is that address in my source column. So I'm going to clear that out. And there are other things that I can do. For example, I can say HTTP. So I can indicate all I want are messages that are HTTP messages. Even though this is protocol SSDP, it actually matches the HTTP protocol and isn't necessarily associated with the typical port 80 that you might see. So this is a little bit different here. I could also say HTTP 2 as an example. I can also say DNS, and then I'm going to get DNS messages, and you can see in the protocol column, it says DNS. So I've got a lot of different ways that I can filter my traffic here in a way that allows me to look at a subset, and I'm just going to stop this, of the packets that have been captured to make it easier to really identify a particular conversation or set of conversations that I want to be looking at, and I can filter out all of the extraneous information that I don't want. One thing that you'll note here as we're looking at this particular packet capture is, first of all, there are over 5,000 packets that we have captured here. Over 5,000 packets seems like a pretty big number, except that in reality it's probably a fairly small capture because you're going to be getting a large number of messages, particularly if you're doing any sort of large-scale investigation. So even though we've got 5,190 packets, which I can see by looking at the status bar on the bottom, and of that 5,190, all 5,190 are displayed, we've got a large amount of communication. What I want to do is figure out exactly what it is that I am looking for. once I have found something, I probably want to really narrow my focus. So here's an example. We were talking about this particular error. This is an acknowledged unseen segment. So there was an acknowledgement somewhere that wasn't noticed. First of all, I can mark or unmark the packet. Now, the other thing that I can do is I can just colorize the conversation. Colorizing the conversation, I can do at any particular layer here. I could say at the IPv4, we're just going to give it a color here that hopefully will stand out from something else. But the other thing that I probably want to do is I really want to maybe follow the TCP stream. And so I could follow this TCP stream here. And now, let me just move this window out of the way because there's not actually anything in it. Now what we've got is in the filter box, it says tcp.stream equals 20. 20 happens to be the stream number that Wireshark has associated with this particular conversation. Now I've got all of the packets that are associated here, and we can see what the source and destination IP addresses are. It really looks like there's nothing but errors here. We've got an acknowledgement, and then there are some other messages that really are all errors. This is one way that I can filter based on conversation. And of course, I can also, as I said, do a conversation filter here. And we could say we're going to filter IPv4. So now I've got this IPv4 filter, which is based on the IP address. So IP address equals 172.30.42.1 and IP address equals 239.255.255.250. So this is a multicast conversation, which I can tell based on the destination address. 239 dot anything is in the multicast range. We can see that we've got a multicast conversation, and Wireshark was very happy to apply a filter automatically for us there. I can just kind of skim down through here, and again, there are a couple of different ways that I can just grab traffic that is associated with a particular frame. So again, I right-click here, and then I could apply as filter. I could do selected, not selected. That's another thing that I could do. Wireshark will apply those filters for me as well. And I could follow this particular UDP stream, for example. UDP here is a conversation between a couple of different parties, and UDP isn't something that we particularly associate with streams because it is actually a stateless protocol. So a stream often is a kind of fluid conversation when you think about it, but Wireshark, in order to use the same language, has UDP streams and TCP streams, and Wireshark can figure out the stream based on the context. So it takes the source and the destination, and I'm going to close this window, and it actually assumes that there's a conversation going back and forth between these two, and so it assigns a stream identifier to these particular frames here. So we've got a number of different ways of isolating specific messages in Wireshark and looking at a particular conversation, whether it's TCP, whether it's UDP, and it's really helpful to be able to narrow that focus down if you've got maybe tens or hundreds of thousands of packets or frames that you are looking at. We're going to talk about investigating latency. Latency is when you've got a conversation that's going on where it looks like there's some delay or some lag. So inherently, there's going to be a particular timing that's associated with a conversation. First of all, let me go all the way up to the top of the packet capture, and then we can look at the time. Now, the time here is all relative to a start time. There is no absolute time that you can see in this particular column. Obviously, we are not capturing at start time 0, which, depending on what your frame of reference is either the beginning of time or it's midnight or whatever. What we're talking about here is the start of the capture. Everything here is relative to that particular start time. So there is actually no time that is captured in any of these headers here. There's no time where we've got this was sent at this particular time. What we are dealing with here is we've actually got what we call a round trip time. The only way that we can identify how long it takes is by capturing how long a message coming from the recipient gets back to us. I'm going to send a message to you, for example. You're going to respond to me. The only thing I've got is the timing difference between those two events, because there's no other way to say a message took X amount of time, because we just don't capture time in any sense at all within the IP or TCP or UDP header fields. It's just not particularly valuable. This time to live field here, if you're looking at this, and you may very well be, the time to live field is the number of hops. It has nothing at all to do with any sense of time as you or I understand it. Because of that, again, we've got a relative time starting at the time of capture. I'm going to go up to my preferences here, and then I'm going to go into protocols. And this is another place where Wireshark can really help us here. I'm going to go down to TCP, and there's TCP right there. I'm going to have it calculate conversation timestamps for me. And if I mouse over this, I'm going to get a little tooltip that says calculate timestamps relative to the first frame and the previous frame in the TCP conversation. And so what Wireshark is going to very helpfully do for us is it's going to figure out the time differential between when it saw the first message within a particular conversation. And so we'll get the differential between those two, and it will also calculate the differential between the message we're looking at and the very last message in the conversation, or the one just previous to the one that we are looking at. I can click OK here, and now if we just apply a filter here, so I'm only looking at TCP messages, if I go into the TCP header, I should actually get a timestamp analysis. And sure enough, that's what I've got here. The time since the first frame in this particular conversation is 30 seconds, and then the time since the previous frame in this particular stream is some number of micro or milliseconds. I'd have to kind of count off from the left there. We've got a way of calculating the value between two conversations, and that's really how we figure out latency, is that we look at the time difference between the different frames or packets within our capture. Previously, we had started to look at time values. So we've got the time column here, which is in seconds. We've got the time that elapses between each of the captured frames. The time here is all relative, and what we had done before was we had gone into preferences, and that's how you get into preferences on a Mac OS system. If you click on Wireshark, you'll get that pull down. On a Windows system, you would go to the edit menu and then go to preferences. We're going to go and just look at the TCP setting here under protocols. And remember, we had done calculate conversation timestamps. Well, that's going to be important here as we start looking at another way of looking at time information. So if I go to a TCP message here, and if I go down to time since previous frame in this TCP stream, if I right click on it, you'll see I'll get apply as column. And as soon as I do that, then we get a column up here just to the right of protocol that says time since previous frame in this TCP session. That's only going to show up in TCP messages, of course, because we're looking at TCP streams. As with any other column, I can sort based on that particular column. Sorting based on this column is going to allow me to take a look at messages that may have really high time values. As I'm just kind of scrolling down through here, they're all more or less the same. If I found one that was really out of whack, then what I could do is to start doing some investigation. So you can actually see that these are starting to increase. So we're not as unified or consistent as we were seeing initially. So now we're starting to get up into really long time frames here. If I were to, for example, go to 46 seconds and I wanted to maybe see what's going on there, I could apply as filter here and see if there are other messages that are involved in that particular conversation, and then maybe see what we've actually got here. Or, of course, you could also do follow TCP stream, which would then just give you that conversation. So that, of course, is a different way to go. And of course, with that, you still get this particular column so that you can kind of see the conversation as it's going along. So what looks like is going on here is that we're just generating errors because we're missing something. Nothing particularly to worry about there. But of course, you can use this column with larger packet captures to really see what the difference in the conversation is with respect to time values. Often you'll find that it's probably pretty consistent. If you start to get some congestion in the network, this is where you're going to start to see latency showing up. And so as you start to see this time since previous frame increase in value, it could be a suggestion that you're having some issues in your network, and that may be something that you want to look at a little bit more deeply. Now, previously we have looked at display filters. And display filters are really good at filtering out all of the stuff that you don't really care about. But they're also really good at narrowing in on very specific information. And there are a lot of values that Wireshark knows about. So, for example, one thing that we could do would be to look for a particular sequence number. Wireshark actually does something with sequence numbers where it shows you a relative sequence number rather than the actual sequence number. The reason for this is because the sequence number should be a random value that then increments. And so what Wireshark does is it takes the random value as its base, that becomes 0, and then it shows you the relative values as the sequence number continues to increase. What we're looking at here with 0 is I'm going to be looking at the very first frame in a three-way handshake. What we've got here is a case where the sequence number is 0. Now, the next thing I can do, once I've got the TCP sequence number equals 0, so I've got the initial SYN message, what I'm also seeing here are the acknowledgement messages as well, because the sequence number there is 0, because the server is sending its own sequence number. I could say, in order to get just the syntax, I can say, and TCP ACK equals 1. So now all I'm getting here are the syntax from the TCP three-way handshake. There are some interesting things that we can do with filters using all of these values that Wireshark actually knows about. Here's another one, for example. We can look for ping messages here and say ICMP type equals 8, and that's going to be an echo request. And I need my two equal signs here. So now if I say ICMP type equals 8, all I get are requests. What I can also look for is ICMP dot resp not found. So I can look for cases where I sent an ICMP echo request and I didn't actually get a reply, and I need the and in there. We didn't actually get one of those. Let's just see if we got cases where there was a response. So the resp in is that there was a response in the packet capture that we've got here. So there are a couple of cases where we can do some really deep analysis. You can also do UDP, and if I type the dot, it will immediately pop open some suggestions here for values that I can be checking. So anytime you don't really know what values you may be able to look, so for example, IP, I can do IP dot, and then it will immediately pop up all of these values that we can be looking for here. You can do really complicated display filters, and remember, you can use and if you want to do a couple of checks. You can also use or. You've also got the capability of using not. The different Boolean operators are certainly valid here within the display filter. So you can really narrow in and get some very, very specific and detailed results from your display filter. Now, as we've seen, Wireshark is really good at digging deep into packets, finding out really useful information, and then displaying it for you and giving you the ability to really dig into the analysis without having to worry about a bunch of other things. So one thing that we can do, again using display filters, is we can look for specific features of an HTTP message. So one thing that I could do would be to look for the request method, and let's say I want the request method to be a GET. What I'm getting in response here are all of the GET messages that are going out to the different web servers that are out there, and we're just looking at the GET message. The other thing I could do would be to say http.response.code equals 200. So now what I'm going to get are not only the gets, but also the responses to those gets. So I'm getting all of my 200 OKs. That's kind of interesting, but let's say you are looking for a very specific error. So I could say http.response.code equals, say, 400. Or we could say 404 or any of the 300s, so 302, for example. So that's a pretty common one. I've got some moved temporarilies here. This is actually going to tell me where the request moved to. This is going to be the response that I've got. And actually, Wireshark is giving us some tips here where the request is in frame 847 and the next request is in frame 872. I can look for error response codes and then have Wireshark actually guide me to the frames that I need to look at in order to really see the full conversation. You can see that we can do some very detailed things with looking into the HTTP method, and we could look for accept languages. We could also look for auth basic, and that's going to look for basic authentication. Basic authentication is actually useful to look for because it's in clear text. So if we wanted to look for basic authentication, and in this case we're not actually getting any, then what you would pop out here would be any frames where there might be usernames and passwords in the clear, and that may actually be something that you'd want to look for. You can look deep into HTTP messages and get a lot of information based on the HTTP header. And then once you've gotten into the header, you can parse it out by component. For example, you've got the request line, the request method, the request URI, request version. And for example, we could look for request version equals HTTP/1.0, for example. And we've actually got some HTTP 1.0 as opposed to 1.1. So if I were to look for 1.1, I should get a lot of them back here because most of the communication is going to be 1.1. The move temporarily, since it's a basic thing, that's just going to be 1.0. We can look deep into HTTP methods using the display filter, as well as looking into IP and TCP as we had done previously. The filtering capabilities for Wireshark are really quite powerful, but it can be a challenge to remember all of the things that you can do with it. What I want to show you here is the expression button. If I click the expression button here, we'll get a dialog box that pops up, and then we can just build an expression by clicking through a few things. Here are all of the field names that Wireshark is aware of, and I'm just going to skim down through here. We can get into IP in here. So IPv4, for example. Now we've got IP.addr. And if you want to know what any of these are, this is a good place to actually get a very short description. So ip.addr is source or destination address. And then we've got ip.checksum, ip.checksum-bad, and then ip.dst, and so forth. I could do that, and then I could say equals, and then my value would be 10.14.15.42, for example. Now, the other thing that I could do, if I click here, it's going to populate it, and then I could apply the filter. So we've got this right here, that's going to be our equal. And I'm going to go back into the expression here and talk briefly about the relationships. So I can say is present, I could say equal, not equal, greater than, less than, greater than or equal to, less than or equal to. I can also do contains or matches. So in the contains or matches case, we are looking for a particular string in the case of contains, or you could use a regular expression, which would be matches. And regular expressions are really outside the scope of this. It's a very deep and dense subject matter that entire books are written about. But you can certainly use regular expressions if you would like to. You don't need to use regular expressions or even know anything at all about regular expressions, frankly, to be able to do some powerful filtering within Wireshark. Now, the other thing we can do here is I can say and then I could say TCP dot source port right there equals, and let's say 80. So for my Boolean operators, I could use and or, and typically that's going to be enough to be able to get you what you need. So again, I could say and here, and then I could go back into my expression filter. Keep in mind, I can also use not equal, which is going to do some exclusion for you as well. Remember, I've got is present, equal, not equal, greater than, less than, greater than or equal to, less than or equal to, and then contain. The greater than or equal to would be really useful for doing something like TCP.source port is greater than or equal to, let's say, 1023. So now what I've got is any case where the source port is greater than 1023, which means I have something outside of the privileged port range. Now I've got all of my ports that include that. So in here, just to be very clear, I could say and TCP. Or for example, I could say or UDP just for fun. So now I've got any TCP packet that's got a source port greater than 1023, or I've got UDP packets as well. So if I were to skim through here, DNS, for example, is a UDP packet. So building expressions can be really easy if you want to use this display filter expression here and get all of the field names. And if you really aren't sure what you're looking for, you could use the search box as well, and that could really help you narrow down the scope for the different field names that maybe you are looking to use. We're going to continue to find ways of looking for traffic that you may want to investigate a little further. One thing that you want to do maybe is find some suspicious traffic on your network. Of course, there are a handful of ways of doing that. We can look for the black lines, as we have talked about before. And of course, you can filter on all of these looking for maybe suspicious source and destination addresses. You can look through the info. You can sort by protocol here. Another thing that we can do here is I can go to the statistics menu, go to protocol hierarchy. Now, when I look at protocol hierarchy, what I'm looking at here is all of the different protocols that have been captured in this particular session here. You can see that at the very top, we've got frames. Every single thing that we've got here is a frame. And we've also got all Ethernet traffic. That's not surprising. It would be unusual to see something like token ring or ATM or something along those lines. So my layer 2 protocol is Ethernet. So underneath that, of course, we've got Internet Protocol version 6. underneath IPv6, we've got some pretty common things. We've got UDP and we've got TCP, and then, of course, there's ICMP v6. Now, I want to look at IPv4 down here, and under here, there are a few things that maybe you want to look at. We've got Teredo IPv6 over UDP tunneling. That seems a little unusual, not completely out of the realm of possibility, but something I don't particularly expect on my network. So that may be something that I want to look at. On the other hand, it's only 2 packets, and so maybe that's not really such a big deal. Underneath there, we've got NetBIOS name service, NetBIOS datagram service. Okay, so I'm doing some file sharing on my network, completely expected. HTTP, of course, domain name system. And then if we just continue to scroll down through here, there's something that catches my eye a little bit here, and that's Internet Relay Chat, or IRC. It's only 279 packets, so it's not really a lot. On the other hand, I wouldn't commonly expect to see IRC on any network. So the fact that I'm looking at a number of Internet Relay Chat messages going back and forth, something close to 300, suggests to me that somebody on my network is on IRC, and given the number of packets, probably isn't particularly active on it, but they're on an IRC server anyway using an IRC client. So that may be something that I want to look at here. The other things that I'm looking at, HTTP, NN, PNG, JPEG, GIF, all of those things completely expected. But if you do this protocol hierarchy, it's a really good way of locating protocols maybe that you don't necessarily want showing up on your network. And then, of course, once we have located that, we could do apply as filter selected, and then I should get all of my IRC messages, and I'm just going to close this, and sure enough, that's what I've got. It certainly would have been easy for me to just type IRC here, but once I'm there, I can have Wireshark do the work for me and then create that filter automatically. We're going to take a look at expert information errors now. If you want to look at expert information, the quickest way is just to go down to the bottom here, and you'll see that there is a red dot. The red dot indicates that there is an error somewhere in the packet capture. And so I'm going to click on that, and it's going to pop open the expert information. If I go to my error here and just open up the first one, it looks like there are 26 errors in the IRC protocol. So we're looking at prefix missing, ending with a space here. These are the frame numbers, and of course I can go to any of them here. And then if I need to, let me just close this up. I can go to frame 733. That's this response right here. You can see at the very bottom, it looks like we are missing some information. We've got a response, but it looks to be incomplete. If I look at these other responses here, it says the prefix is irc.underworld.no. The command is 352. And then I can look at command parameters. If I look at the very bottom one, it looks truncated here. And so it could just be that there wasn't enough to actually send this, and this looks like a bad protocol command because somehow the frame actually got truncated in some way. If I go back here to errors again, I've got a malformed packet here in a different protocol, and this is the kink protocol, and that's the Kerberized Internet Negotiation of Key. And so that's a way of getting a security key between a Kerberos server and the client. We're using the kink protocol. And again, if I click on this, it takes me down to the correct frame. So I'm going to close that out. And this is the frame right here, 2018. Sure enough, it says malformed packet exception occurred. And I can pop open the kink message here. So this down here is actually what Wireshark is telling me. This is not something that was captured. This is actually something that Wireshark has added in. This is actually the portion of the data that we're looking at here. So the highlighted section in the bottom is the data in the application part of this particular frame. And then, of course, underneath that, Wireshark again is very helpfully pointing out that there's a malformed packet here. And a malformed packet is one that doesn't follow the expected protocol. Kink has a specific set of directions or protocols that need to be followed so that Kink can actually work correctly. What's happening here is there is a packet that doesn't match those rules. And so as a result, it looks malformed to Wireshark. A malformed packet could potentially cause errors on systems, including crashing applications. And so this is one good reason to pay attention to the errors in Wireshark. Again, we've got warns down here as well, but considering the number of errors that we got here, that's also really important to look at and investigate those particular messages within our packet capture. Now, one thing to keep in mind as you're working with Wireshark is you've got entire network communications here. So everything that goes over the network, you have sitting here inside Wireshark. Why do I say that? As an example, let me just do a little filter here. So I'm looking for portable network graphics. Now, what do I have? If I go down to the very bottom here and I scroll through HTTP, at the bottom of that, there's a ping file. So I've got a file sitting here that I actually have the ability to just export off and maybe be able to open it up. I could export packet bytes at this point, which would allow me to dump the bytes from a particular packet out to a file. There are a number of other ways to export information, and if I go up to the file menu again, I could export packet dissections as plain text, as comma-separated values, or as C arrays. And the C in quotation marks here is the C programming language. So I could also grab a number of packets, and I could select those, and then what I could do would be to export specified packets. So if I go to selected packets only, as an example, I could just dump those out to a file. So there are a handful of ways of getting data out of Wireshark, and it isn't necessarily entire packet captures because, again, keep in mind that you're grabbing everything going over the wire. And so if there were, for example, files that had been transmitted, whether over HTTP or maybe using the server message block protocol to share files across your local network, all of those files are going to be intact within your capture, and it's really just a question of finding the right method to actually extract those. We've looked at a couple of ways that you can locate information here within Wireshark, but there are other ways that you can actually export files in particular, and we'll show you another one coming up. Now, we've looked at a couple of different ways of extracting information from Wireshark. If I go to the file menu, I can do an export specified packets. I could do packet dissections, but there's something else that's really useful that I can do. Again, if I go to the file menu, I can export objects. So I could look for SMB objects as an example. And in this case, I don't actually have any because I didn't get any off the wire because I wasn't sharing any files here. But another thing that I can do is, again, if I go to export objects, if I look for HTTP, now what I've got here are a whole bunch of objects. So we've got some GIF files here, for example. So if I select that message right here, that's in packet 663. And if I go to packet 663, we go through HTTP, and then here's the GIF file that's right there. And the image is actually right here. So if I were to go back up and select this, you can see the image is all right here in the blue section down below. If I were to, again, go back to export objects and go to HTTP, what I can do is I can locate a particular file maybe that is passed through, and I could actually export that particular file if that's what I wanted to do. Let me just find a PNG file, for example, or even better, here's a JPEG. So I've got a JPEG file, and I can save that. If I save that to downloads here, and now let me just go to my downloads directory, and this is the file, and you can see this is the JPEG. All I had to do was locate the file name that I wanted out of my HTTP object list, and then all I've got to do is say save. Wireshark pulls the data that's associated with that particular file and then saves it off to disk for us. So if there are files that have been transmitted using HTTP, you can grab those. Again, if you had some that were transmitted using the server message block, then Wireshark is capable of extracting those as well. In this case, I didn't actually have any that had been transmitted that way, but if I did, I certainly could have saved them off. And then I've just got the file on my disk, and Wireshark did all of the difficult work of extracting the file bytes from potentially multiple frames so that we've got just the resulting file. Then we can do whatever it is that we need to do with that file. Now, we've taken a look at how to do a lot of analysis and use Wireshark to do some of that analysis for us. Wireshark is also really good at extracting data from the packet capture and then presenting it in a really useful visual way. There is a statistics menu in Wireshark, and I'm going to click on my statistics menu. And then what I want to do in this particular case is I'm going to go to the endpoint statistics. What I get with the endpoint statistics is I've got all of the endpoints that have been located within this particular packet capture. Now, you can see across the top, I've got TCP, Ethernet, IPv4, IPv6, and UDP. TCP, these are all of the IP addresses that communicated in a TCP conversation. You can see these are all just addresses, which isn't necessarily helpful. So I'm going to go down here, and I'm going to do name resolution. What should happen is that we should actually get the names to resolve eventually to host names rather than simply IP addresses. Now, the other thing that we've got here is port information. The port information, again, is just a numeric value. In this particular case, I see port 443, which is the SSL TLS port for web traffic. We've got other ones here. So my Ethernet, I've actually got 31 separate MAC addresses that show up within my packet capture. So I've apparently got 31 devices that are communicating on my network because we saw 31 MAC addresses. If I go to IPv4, I've got 77 addresses here that were IPv4 communications. And then IPv6, I've actually got 51 IPv6 addresses. Again, if we go back to the TCP one, I've got a bunch of IP addresses on the left-hand side, but what this tab here is breaking out is the TCP communications. Apparently, there were 286 conversations or endpoints based on the port number, which is what is associated with TCP. Same thing with UDP. There are apparently 415 specific endpoints, meaning an IP address and port combination. So we could have multiple IP addresses associated with different ports, which is exactly what has happened here. You can see 172.30.42.8 shows up multiple times for an IP address. That's because there were multiple ports that were communicating on that particular IP address. When we're looking at the TCP and UDP endpoints, you want to think in terms of what those particular protocols do. those particular protocols are responsible for ports. And so even though there are IP addresses associated with them, we're really looking at the port information. If all you care about is the IP addresses themselves, you want to go to the IP tab, either IPv4 or IPv6, depending on which one that you really care about. So we've looked at endpoints. The thing is, though, that that's really only half of the story when we're talking about the communications that are going on through Wireshark. These endpoints are just that, they're endpoints. A communication stream is bidirectional, and all we've got here are a list of really kind of unidirectional things. So we've got IP addresses, congratulations. What I really want to know is which IP addresses are communicating with which other IP addresses. Again, I'm going to go to the statistics menu, and in this case, I'm going to open up conversations. Now, conversations, that's bidirectional. You can see already we've got address A and we've got address B. It does pop open to TCP. And so what we're looking at here are the port combinations. So I've got IP address 172.30.42.10 on port 55870 communicating with 172.30.42.13 on port 445, which is the CIFS or Common Internet File Service port. And so there are some sort of communications that are going on my local network around file sharing, which doesn't necessarily mean the files are being exchanged. CIFS and SMB are really communicating on a pretty regular basis around the network, exchanging information, just kind of being chatty. Hey, I'm here. Hey, I'm here. So we would expect to see those sorts of things. Here I've got web communication. And again, you can see the IP addresses are showing up in multiple locations. The reason for that is because even though the IP address on the server end is the same, my source port here that I have initiated the communication with, 63,815, is different than the next one down, which is 63,813, which is different from 63,811, and so on. So even though my IP addresses are the same, my ports are actually different. If I want to just worry about IP addresses, now I can go to this tab over here. Now all I've got is address A, address B, and here I can look at the number of packets that were exchanged. Again, as we have done with other cases here, we can sort based on a particular column. This particular pair has actually communicated with 1,107 packets for a total of 719,000 bytes. What we then end up with is a list of just IP addresses, and this is an aggregate. So if I go back to this tab over here, the IPv4 tab would actually consolidate these communications right here, and this one, and this one, and this one. All those four port combinations would be consolidated into one set of communications on this tab. And the reason for that, again, is because on this particular tab, we only care about IP addresses. We're not breaking it out by port. If I go to the Ethernet tab, again, you can see address A, address B. Those are MAC addresses. One other thing to consider here is I've got bytes going from B to A, and I've also got bytes going from A to B. We're breaking out the communication that's going on, or the conversation, if you will, into the number of packets that are going in both directions, packets A to B, packets B to A. I've got 558 packets that went one way and 549 packets that went the other way. And out of that, we get the total number of packets, which is 1,107. Same thing with the bytes. And then if you really want to get very fine-grained about this, we can look at the relative start, and then we've got the duration of the conversation, and then it also breaks out bits, which is really just multiplying your bytes by 8, of course. And so that's how we get the bit rate and, of course, the byte rate as well. we can really look in great detail so that we can look at the two systems that are communicating the most within a particular packet capture. That can be really useful information to have. Wireshark has a lot of statistical capabilities, including the capability to generate graphs for us as well. So if I click on the statistics menu, I get these choices here. Now, one of these is an I/O graph, and I'm going to pop open the I/O graph. This is going to show me the number of packets per second on the y-axis here, and on the x-axis, we've got time. So you can see as I drag my mouse to the right, it actually tells me which packet that I'm at. Right now, I am at click to select packet 3316, which you can see just below the graph here. What we've got is all packets, which are black, and then we've got errors, which are blue. And I could change my interval here if I wanted to get a little bit more fine-grained. And let's say I want to do every 10 seconds. So now you can see that we've really got just a bar graph here, and that's what it says right here is because I had clicked TCP errors. If I unclick that and I say all packets, then I get my line graph back, and I can again change my interval based on my line graph. The further out on the interval I go, the less granular, obviously, I get, and I get something that looks very different. I could do time of day here, which would be, I'm going to go back to 1 second here. So rather than just the packet number, I actually have the time. So if I uncheck the time of day, I've got time elapsed from the 0, which is the very beginning, and now I can just kind of scroll over to the right and get the packet number. And then if I click on that packet there, it pops me underneath. If you didn't see it, let me try it again, but it pops me underneath to that actual packet or frame number. I'm going to click right here, and underneath the graph inside the actual packet capture, you'll see that the packet number or the frame number is actually changing, and Wireshark is going to that particular selection for me. I've got the ability to actually add additional display filters here. Any display filter that I wanted to look at, I could actually add in here. Just for fun, we could say source port, and then I could pick a color here. And then if I click that, we've got a line chart that I could change to a stacked bar. I could make a lot of changes to my graph style as well. You can add in different types of charts into the I/O graph if you want, just by creating a new display filter and then changing the color, making a different style. Of course, you can also change the y-axis here to bytes or bits or sum, max, min, and so forth. And then I could add in smoothing. I could change my y field. I can create some really interesting graphs using Wireshark's built-in capabilities here. And once I've got that, I could actually copy that graph and then be able to use it maybe in a report that I'm writing, for instance. We've again got a lot of really powerful capabilities that can help us visualize the data better rather than just sitting here staring at a raw packet capture. We've actually got the ability to generate graphs that may actually show us very specifically what is going on. And here's another one, for example. Here's a flow graph as another way of visualizing data. This is kind of a ladder diagram for a particular conversation. But I've got different graphing capabilities that are built into Wireshark, so you don't have to look at exporting data and creating graphs in Excel, for example. You can do it all right here in Wireshark. One task that's pretty useful is to figure out what endpoints are really active in conversation. In other words, the endpoints that are sending a lot of traffic back and forth. So the first thing that I want to do here, because numbers really aren't going to do an awful lot for me in most cases, certainly my own network, I can probably figure out where things are. So the private address is the 172.30.42 address here that you can see. I can probably figure that out. The other endpoints really aren't going to mean much of anything to me. So I'm going to go to the View menu, and then I'm going to turn on Resolve Network Addresses. And you can see the others are turned on as well. And this is going to help me when I do the next thing. I'm going to go to the Statistics menu, and then I'm going to go to Conversations. This is something that we have looked at before, but now, of course, I've got name resolution turned on. And if I turn this on without doing the name resolution resolve network addresses here, then we're not actually going to see anything, which we had seen previously. You actually have to turn the view network address resolution in the view menu, and then this will actually work. So now what have I got here? Well, I've got a number of conversations that have been going on. How am I actually going to determine which ones are really active on the network? Well, as it turns out, this is really easy. There's a few different ways I could do this. The first thing I can do is I can look at the packet count. So one of my systems here, 172.30.42.13, apparently did a lot of conversing with snugglelove.com. Not really sure what that is. I'm going to guess it's an ad kind of thing here, based on the network traffic that was going on while this capture was in place. So 1,107 packets there for a total of 719 kilobytes. And then it looks like Akamai DNS, something to do with Apple. So it looks like one of Apple's systems going through Akamai was actually pretty active in terms of conversation. Now, the interesting thing here that you'll see, 808 packets, 315K, whereas this one, 606K, so quite a bit more. In fact, almost twice as much, but fewer packets. This means that the packet size was actually larger in this case than it is in this case here. This was a number of smaller packets that totaled 315K, where this was the larger number of packets. So the number of packets was actually a smaller number, even though the byte count was different. And so this is why you may want to actually look at bytes instead of packets. They should align more or less similarly, although they're not going to be exact because packet sizes actually can vary quite a bit. You could get a packet size of 50, for example, all the way up to 1,500, but you could send a lot of smaller packets and then get large packet counts, but smaller byte counts. So we could actually also order based on packets from A to B, in which case my system actually sent a large number of packets to this address here. And then if we go to packets B to A and resort there, then actually it's still the same. So we've got a similar order when we do this. So there are a lot of different ways of looking at the conversation. In fact, all we're doing here is we're looking at the IP layer. I could go to the TCP layer, and then I could order here based on packets as well. So 966 packets. This is an IPv6 address here. And again, we're going to one of the Akamai servers over HTTPS. So we could also look at UDP. And again, we can look at packet counts and we can look at byte counts as well. And again, we've got some variation there. So you can look at active conversations on your network in terms of the amount of packets they are generating as well as the byte counts they are generating. And you can look at it in Wireshark from a number of different perspectives, whether it's IP or TCP or UDP. And then you can look at byte counts, packet counts, and really start looking at who is sending messages to whom, and figure out where the really active traffic on your network is. And again, this is really helpful for a lot of different circumstances. One in particular is if you've got somebody that's really causing congestion on the network, or a number of nodes on your network that are causing congestion, This is one way to narrow down where that large block of traffic is coming from, whether it's one system or a handful of systems. You can really narrow that down looking at the conversations view and starting to do some resorting of the different columns that we've got here. We've been talking a little bit about name resolution so far, and we're talking about mapping IP addresses to host names and vice versa. Now, in order to get locations for IP addresses, I could use whois, but there's actually an easier way to do this. Now, what we're going to look at is using GeoIP. In order to use GeoIP, we need some databases. So one place to get those databases is right here at MaxMind. You can look up GeoLite Legacy downloadable databases, and if I scroll down through here, you can see we get to the download. So in my case, I'm only going to be looking at IPv4, although we could certainly look at IPv6 as well. They do have those databases. So I need to download this one here for the country, and then I need a second database for the city, and then finally, this one has to do with network numbers, and I'm going to download that one as well. So once I have gotten those downloaded, they are going to come in gzip files, and I need to unzip those. And once I have done that, what I need to do is go over to Wireshark, and then I'm going to go to my preferences, and then I go to the name resolution, and then down here at the bottom, you can see GeoIP database directories. Now, I have added mine in already, and you can see that I've created that directory. If I needed to place another directory listing in here for other databases, I would just click the plus, and then I would go add that additional directory. Once I have added in my GeoIP databases and told Wireshark where they live, Wireshark can now make use of those. We are going to look into how we can map IP addresses to actual physical locations, and we're going to do that coming up in the next couple of lessons. We've got the GeoIP databases loaded at this point. We've gone into preferences and we have added the database locations. The other thing that we need to do is go into preferences, and then if I go into protocols here, I need to find IP. And I'm going to look for IPv4 in my list here. And then I need to enable GeoIP lookups. Once I have done that, there are a few things that I can do. First of all, I can say IP, for example, and IP.geoip.country equals United States. So now all I've got here are IP packets or IP frames where the IP address is in the United States. I could also say not. So now what I've got are IP packets where the IP address is somewhere outside the United States. So there are ways now that we can do display filters based on GeoIP. So you can see this is the list of the different parameters that I can do searches on. So I could, for example, say my .lat, my latitude is greater than 45, for example, here. So now what I've got are packets where the latitude for the GeoIP lookup is actually greater than 45. I could also do less than, and then of course this would just be really, really northern climates. What I've got here are cases where the GeoIP latitude that has been determined from the GeoIP lookup is actually less than 45. So the other thing that I can do, not only are display filters, but if I go into my statistics here, and then I go into endpoints, now what I've got are all of the countries and then the AS number, and then I've got the city and the latitude and the longitude. So you can see that all of a sudden we've got a whole bunch of additional information here that we didn't have before. All we've got to do is go into endpoints with our packet captures, and we can get the GeoIP information that's associated with all of these addresses that are available in the database. That's to say that if something hasn't been reported in the database, it won't actually show up here. So, for example, these are private addresses. Those aren't going to have GeoIP entries. There are some multicast addresses that I noticed here that aren't going to have GeoIP entries either. Periodically, you will run across cases where the IP address may not have a GeoIP entry, but for the most part, you're going to be seeing a lot of these countries, AS numbers, cities, again, depending on the databases that you have downloaded and the databases that you are using. I'm going to open up the endpoints dialog box here again. So I'm going to go to statistics and then endpoints. Again, you can see the AS number in the city and the latitude and longitude, and certainly you could look up the latitude and longitude for these IP addresses. It's kind of tedious though. So what we've got here is the ability to just generate a map. And if I click that, then what Wireshark will do will be to just create a map for me, and then it will present it within my default browser. So now I can click on one of these buttons here, and we've got the host name, we've got the city, and then we've got some information. We've got the packets, and then we've got the bytes. So I could go over here, for example, because I happen to know Akamai is in Cambridge, and we were seeing a number of packets and bytes there. So this one doesn't happen to have an awful lot, but there is another dot right here, and that's actually a slightly different one. So let me zoom in just a little bit here and see if we can get some additional dots to show up so that we can get maybe some more data here. So it looks like there's one in New York, and there are the ones that were Akamai here. And then this is the one in New York. So now we've got 34 packets and 6,000 bytes. So again, we've got a number of places that we can look at here on the map, and we can determine where exactly things are. So this does rely a little bit on digging around some in order to find everything. Of course, if you've got the listing where you've got the city name, and you can just look on the map if you kind of know roughly where it is. So here's appspot.google.com, and then we've got some others in that same area down here. So we've got a number of places on the map that we can just kind of click around at. Again, I'm going to zoom back out here so that we can see everything. You will see, actually, the interesting thing is the clusters that go on. You're not seeing a lot here in the middle of the country or over here. You kind of are clustered where more or less you expect to be. So Northern Virginia, for example, Massachusetts, certainly California in the San Francisco Bay Area, and then Southern California, that's reasonable. In the center of the country here, you may find a lot of things located because the center of the country is sometimes where people place backup facilities. So you may find data centers and so forth in the center of the country. That's not necessarily an unusual place to be. Now, if we've got anything that's outside of the United States, and it doesn't really look like we've got anything within this particular packet capture, you can do a little bit of scrolling around the map in order to locate those other areas. So it will map everything around the world if you do happen to have the right databases installed. So those ones that we were looking at earlier from MaxMind will provide information around the world for you. And again, Wireshark will generate this map for you so that you can locate different places and then start getting a better idea of where your systems on your network are attempting to communicate with. We're going to go back to taking a look at protocol hierarchies. If I go to the statistics menu, and then I can go to protocol hierarchy, what we've got here is the entire breakdown of the packet capture that we've got broken down into a hierarchical fashion, starting with the frame. Everything begins with the frame. And again, the frame is the entire unit of capture here. It's called a packet capture, but what we're actually getting, because we're talking about layer 2, is we're getting a frame. So right here, this is a frame, and so forth. You can actually see it right on the very top line here. It says frame 18,161. So we've got our frames, and again, I'm going to go back to my protocol hierarchy. Since everything that we are capturing is a frame, the percentage of packets here is 100%. Not surprisingly, 100% of the packets captured are Ethernet packets as well, because I don't run anything else on my network here. Everything is going to be Ethernet. There's no token ring, there's no ATM, there's no Sonnet, no anything like that. It's all Ethernet. Now, in this particular case, what we've got is IPv4 is 100% of the packets that were captured. Sometimes you might actually see some IPv6. In this case, we don't happen to have anything here that was IPv6. It's all IPv4. And then we just continue to go up the protocol stack. So we've got UDP and then TCP. And the only thing under UDP actually is the domain name system. And we can actually break this down by reordering these if we want. So at the moment, it's ordered by protocols, and we've got UDP, TCP, and then it's broken down from there. But we could actually go by percentage of packets, or we could go by percentage of bytes, the total number of packets. So we can reorder all of these pieces of information based on the column headers. So bytes and then bits, and then we've got the percentage of bytes and so forth. So you can reorder this any way that you want. It happens to be, in this case, that we are ordering it based on the tree view of our protocol, starting at the very lowest layer, which is our frame, and then we go up to Ethernet. And then again, we've got IPv4, and then underneath that, we've got UDP, TCP, and ICMP as well. So in order to really get a good understanding of the types of traffic that are traversing your network, what you can do is look at the protocol hierarchy statistics, and you can actually see the different protocols that are passing by in any particular packet capture. So we've got a breakdown all the way up to the application layer. We've got the extensible markup language. Of course, we've got HTML as well. And we've got some presentation layer stuff here, like GIF, for example, and then JPEG and PNG. It also indicates that we've got secure sockets layer, just as another indication there of a type of packet that's been captured. In this case, it's probably HTML, but Wireshark really has no good way of knowing that, because it can't decode those SSL packets, because the certificates and the encryption keys are actually stored on the endpoints. They're not stored within Wireshark. The protocol hierarchy statistics is actually a really good way of viewing the data that you've got within Wireshark and getting a good handle on the amount and type of traffic that's actually passing across your network. In this case, we're going to go back into the protocol hierarchies again. So statistics and then protocol hierarchy. Now we can go digging through again and see if we can see anything that may be a little bit suspicious to us. So the first thing that jumps to mind here is Internet Relay Chat. That may be something that could be a little bit suspicious here. The other thing that catches my eye is something here that's just data. And there really isn't an awful lot else here that jumps to me other than here's one that just says data as well. And I could apply this as a filter in order to identify all of those. And let's actually do that, apply as a filter here. And now I can go back here and see what we've got. So all of this is my UDP data, although here's some TCP data that's stuffed in the middle here as well. So these kind of look a little bit like maybe orphan frames that don't necessarily belong to particular conversations, or Wireshark couldn't identify them very well. So that may be something that's worth looking at. So I'm going to clear that out, and I'm going to go back up to my protocol hierarchy. Now, if I really want to look at the internet relay chat messages, I could apply as filter and then selected. Now I've got all of my IRC traffic here as well. Now, the other thing that I want to look at, and again, I'm going to go back up to my protocol hierarchy, and I want to take a look at all of the secure sockets layer traffic. And let me actually do this one here. So I'm going to say selected, and that's going to say SSL. So I can go skimming through here and just see who it is that we are communicating with. So in this case, it looks like this is primarily Google, although we've got keyvalueservice.icloud.com. Okay, so that's going to be an Apple thing. So we've got some communication. All of this actually looks pretty good, although here's one that may catch your eye a little bit. So it looks like there's a Tor node, and Tor is the onion router, and it's used for browsing in an anonymous fashion. So this may be something that indicates on your network that somebody's doing something they don't want to be seen. So this is TLS version 1.2. It's encrypted, but it is coming from a Tor node, and we can also see the other direction as well here. So this may be another case where you may want to investigate a little bit. This didn't pop out directly from the protocol hierarchy, although since I knew what I had done, I kind of knew what I was looking for, and that may often be the case when you are doing investigations or analyses on your network, is you may know a little bit about what you're looking for, and so you can take some guesses as you go through the protocol hierarchy. In this case, I went back to the protocol hierarchy with the display filter in place, and now what I'm getting is only the frames that are showing up within my display filter. So the protocol hierarchy that shows is based on what's showing within Wireshark. So if I clear that out and then go back to my protocol hierarchy here, everything shows back up, and you can go back to your investigation within the protocol hierarchy to identify maybe some traffic types that you weren't expecting or were hoping that you didn't see. You may want to find errors within your packet capture really quickly and easily, and you may want to actually see them in terms of a particular timeline. So one way to do that is if we go up to statistics here, and again, we're going to go to IO graph. Right now, I've got nothing turned on. So if you go down to the bottom here, you can see all packets, TCP errors, and then all packets. And this is the TCP source port that we had looked at previously. I'm actually going to remove that. And here you can see in the top line, the display filter is tcp.analysis.flags. So what I can do is I can turn that on, and now you can see where we have all of the cases where the analysis flags have been set, meaning there may be an error there that you want to take a look at. So once you have identified the errors, you can actually see where we've got a really large number of errors that are occurring. So it looks like, for example, right here, we've got a fairly large number of errors that are happening. And if I select that and then go back to the window here, you can see that we've got a number of errors in the display window behind, because the black there you can tell is an error. So again, a really quick way of identifying a large number of errors visually is to go to statistics IO graph, and then when you bring up the IO graph, here the TCP errors one is there by default, and in order to see them, all you need to do is just check the TCP errors. If I want to see a graph of all packets, I can do that. That would give me a sense of spikes in traffic. And then I can look at TCP errors on top of that. And then I can see cases where there are a large number of errors here, but there's also a spike in traffic as well. I may want to look at cases where there are a large number of errors, but no spike in traffic, just for some sort of anomaly. You're not always going to see more errors when you see spikes in traffic. Obviously, here's a good example where I've got a pretty large spike in traffic and no errors at all. So cases where I've got a large spike in errors and traffic is low may mean that something very specific is happening there, and we can go and take a look at that. It's going to take me directly to that set of frames. I can go over here and actually see what's going on. If I click on this, I can go to the expert information and just see what we've got going on within our packet capture. So there are different ways of looking up information. I can go to the expert information. I could also go to the I/O graph and just kind of see where the errors are occurring, and then maybe look for large clusters of errors so that I can do a little bit more investigation within that particular time window. We're going to move into some very specialized packet captures. We've looked at various application protocols like HTTP or IRC. What we're going to look at now is actually a set of protocols that come together to perform application functionality. So we're going to look at voice over IP or IP telephony. And there's a couple of different protocols that you may run into when you are looking at voice over IP or IP telephony. The first one that we're going to look at, we are going to look at SIP. Now, SIP is the session initiation protocol, and it's actually text-based, which makes it very easy to read. If I come down here, you can actually see the message. So if I click on that, what you can see is invite SIP : and then there's a destination address, and this is very HTTP-like, and the reason for that is because SIP is based on HTTP, and Wireshark, as usual, does a great job of pulling the message apart, and what this is actually the beginning of a conversation. So if you were looking for VoIP calls, you might look, for example, for SIP, and again, we're going to go back to the protocol hierarchy here. And if I go through the protocol hierarchy, we've got actually the session initiation protocol right there. And I could do apply as filter selected. And then all I've got are SIP messages right there. So, of course, I could also, if I wanted to, I could just say SIP, and there are all of my SIP messages. Now, the other protocol that we could see when we are talking about voice over IP or IP telephony is H.323. So I'm going to look at an H.323 protocol capture, and in this case, what we're looking at is we're actually looking at a binary protocol. And by binary protocol, I mean a protocol that is not text-based. So let's actually take a look at what we've got here. And I'm going to go to the H.225 section here. So H.323 is actually a series of protocols, and it encompasses things like H.225. So I can open up the H.225 here, and if I were to select this, a lot of it really wouldn't make much sense to you. So what we require is Wireshark to actually pull some of this apart for us. And you can see it's got the protocol identifier here, and we've got a source address, and then we've got call identifier information, and then a call type, and we've got a number of other parameters here within the H.225 message. Now, these are not things that you would normally be able to just read, for example. So here's the protocol identifier. This doesn't jump out to you necessarily immediately as something that you would just be able to read. Or you could look at this active MC, for example, or any of these others where I've got source call signal address, and we've got a port identifier and an IP address here. So what we've got are a number of parameters within H.323 that are really much easier to have Wireshark pull apart for us rather than trying to visually identify what the different components are. Certainly you could look at this 0A, 01, 03, 8F, and yeah, you could convert that to 0A is 10, 01 is 1, 03 is 3, and then 8F is going to be 143, and the reason I know that's because I'm looking at it right here. That's the source address. So you can see that what we've got are a number of parameters here that Wireshark is just simply better at pulling apart for us. Now, that's not the case with SIP. As I said, SIP is completely text-based, and you can identify these calls here as, for example, I could say H.323, and I'm not actually going to find anything there. So the other thing that I want to look for is H.225. And if I hit enter there, I've got my H.225 messages. And then there are other protocols that are involved as well, including H.225 RAS. And in this case, we don't actually have any of that particular protocol. But as I said, H.323 communications are a result of a number of different protocols. And here's actually one that you will see in both H.323 as well as SIP. This is the real-time protocol. And this is where the media traffic is carried. So this is the actual voice or media part of the telephone call right here. So if you've got VoIP phone calls, you can look for SIP, you can look for H.225, you could potentially look for H.323 or the other H.323 based protocols in order to identify the different components. And then we can find other ways of identifying particular conversations, and we'll do that coming up next. At this point, I know the protocols that are being used for voice over IP, but what I really want to do is I want to pull out the conversations that are going on. So there's a menu that is for telephony, and I can go to the telephony menu, and I can say VoIP calls, and what we've got here is one VoIP call. So we've got this one here. It says the protocol is H.323. There are a total of 28 packets. And then I've got the initial speaker, which is 10.1.3.143. So we've got the telephony here for VoIP calls. The other thing that I can do here is I can check for RTP streams. And this would be based on the conversation. There should actually be two RTP streams, one in either direction. And this I can actually use to give me some information about the conversation. So I should be able to get things like lost packets, which I've got right here. And then the other thing that you might want to do is do a little bit of analysis for jitter and latency. So that would be related to the quality of the conversation. Now, I want to go back to the SIP call at this point. And I'm going to open up my SIP call. I can do the same thing using SIP as I did with H.323. Again, I'm going to go to the telephony menu, and I'm going to bring up VoIP calls. And here, it looks like we've got three separate conversations, which could entirely be true, or it could be pieces of the same conversation. In this case, though, what we've got are start and stop times, so this does suggest we've actually got three entirely separate conversations that took place within this particular packet capture. So if you're looking for conversations, you go to the telephony menu, and then you can go to VoIP calls to bring up your VoIP calls. And again, with this one, I could look at my RTP streams here and see whether we've got RTP streams that are going on. And sure enough, I've got three separate RTP streams that have been captured within this particular packet capture. At this point, we've taken a look at the telephony menu, and I'm going to look at it again here. So what we've got are a number of different categories here that are based on different types of voice over IP calls or telephony calls. Some of these are going to be based around SS7, for example, signaling system 7. Some of these are going to be based around other types of telephony. What we are interested in here are our VoIP calls. So I'm going to bring that up. And then what I could do here is I could prepare a filter based on this in order to isolate just this particular conversation. I can also look at my SIP statistics, and I'm going to scroll down towards the bottom here. And so I should see a total of 4 200 OKs that were sent. I've got 2 180 ringings and then 2 100 tryings. I'm going to see 3 SIP registers here. And then I've also got an acknowledgement message and an invite. So these are the different response codes as well as the requests. And I could actually create a display filter here as well within my SIP statistics. Now, what I've got here is the minimum setup, average setup, and max setup. I don't actually have any values for that. If you had a longer capture, you might actually get more statistics, although we've got one here. So it took about 8.5 seconds for this particular acknowledgement. So that's my minimum and my average and my maximum because I only had one of them. These others didn't register as anything that we're going to keep track of within these time values here, but you could use the SIP statistics in order to get some additional details around your voice over IP calls. And I'm going to go back to my H.323 example here, and I'm going to go back and I can look at H.225 here. And this is similar to what we had in the SIP analysis where we've got the counts for different messages. So right here, I've got a call proceeding, and that's a little bit like a ringing message. And then we've got a connect message, and that suggests that somebody picked up somewhere. I've got an alerting message, and then these others are all just zeros. But you could use this right here as a way of gathering additional information about your voice over IP calls. And as I mentioned previously, I could select one of these and then say analyze. And from that, I can get details around jitter, and I can get my deltas on it. My jitter and latency, as well as dropped packets, as I've said, is going to be really all about your call quality. And so you can get a good handle on how well the call quality was, the audio quality was from this particular set of data here. And the reason for that is because if you've got a lot of jitter or a lot of latency, it's going to end up with calls that really sound kind of choppy. And if you've got a lot of dropped packets as well, for example, these lost messages here, in this case it's just one, but if you've got lost messages, that's a piece of data, even though it's microseconds long, that's a piece of data that didn't get there. So the listener never heard that particular, say, 20 millisecond chunk of audio. So there was something there that was missing. So from this, you can actually get details around how good your call quality is. And here's another one that was a wrong sequence. So in order to get information around the calls, as well as the RTP streams and the audio quality, you can use this telephony menu as well. And you could use the RTP menu as well as getting details from the SIP statistics, as well as the H.225 statistics that we looked at as well. When you're troubleshooting VoIP calls, one of the most tedious things is graphing out where all of the messages are going to, where they're coming from, and who they have gone through. In a typical voice over IP call, you may actually pass through several segments or several network devices that are commonly called proxies in order to get from one endpoint to another. It's not generally just as simple as, hey, I want to call Alice or Bob or John, for example. I'm going to bounce through a number of gateways or proxies in order to get messages to them because I don't necessarily know exactly where they're located. And so I need these registrars in these proxies in order to do the location for me. So if I'm bouncing through multiple network communication devices, then I really need a good way of actually providing me a visual look at what these calls look like. In that case, what we need a ladder diagram, and what Wireshark calls it here is a flow sequence. In order to get there, I went to Telephony and I went to SIP flows. Now I can click on flow sequence and I get something that looks like this. The reason it's called a ladder diagram is because you've got a sequence of rungs going from left to right. Now, this goes in time order from top to bottom, and depending on the number of nodes that we are going through, I may take up a number of rungs on the ladder. In this case, we've got 3 devices by the look of it. And so what I am doing here is I am sending my invite, which is a SIP message. And if I look at the very bottom here, right underneath this particular window, I'm going to click here and then pay attention to the very bottom of the screen where there's text. If I click here, you'll see that what Wireshark has done is it has selected the message that is associated with this invite. And I can keep clicking through the call, and I'm going to get the 100 trying message and then the 180 ringing. And you can see that these are all coming back here. The 100 trying and the 180 ringing and then the 200 okay are all coming back to the device that did the capturing or that initiated the invite more specifically. So I've got the invite coming out of this particular system that did this capturing, and then it received a 100 trying message, a 180 ringing, and then a 200 okay, which suggests that the party picked up. At that point, we start initiating the RTP, we get an acknowledgement, and then the RTP back. So this is a ladder diagram. As I said, this is really helpful for really getting a visual look on what the call looked like, because it's really difficult to kind of visualize it just seeing a bunch of numbers within a packet capture. I can bring up another flow sequence. This one's even easier. This is just a register that's coming in and then a 200 OK that's going out. You'll also notice here we've got port information. So 5060 and 5061 are the 2 ports. 5061 would be the source port and 5060 would be the destination port. The reason I know that's because of the arrow. So the source port would be where the message originated from, and then the destination port would be where the message is going to. So the ladder diagrams are really, really helpful to have. Again, if you're doing troubleshooting of voice over IP calls, this is incredibly valuable to be able to get these flow sequences or these ladder diagrams. And all we've got to do is use Wireshark. It does it automatically for us. Nothing really complicated about it. If I go to the telephony menu and then I go to SIP flows, I've got my flows right here. And then all I've got to do is select one and then do a flow sequence. And I can get my ladder diagram and really be able to see where messages maybe are getting lost in the communication. As I've mentioned here, we actually have audio within this packet capture. If I type RTP, all of these messages are the real-time protocol messages that are going back and forth between the 2 endpoints. Included within there is PCM audio, which is pulse code modulation. So this is digitally encoded audio that is being transported between the 2 endpoints. It would be really great if we could actually extract the audio. And as it turns out, that's really easy as well. Again, I'm going to go to the telephony menu, and this is my SIP flow here. I can click on this here, and I can just say play streams. This is going to pop up an RTP player, and it will actually play the audio for me. So this is really convenient. I don't have to do anything around exporting any objects from the RTP streams. All I have to do is select one of these and then just play stream, and the player will come up, and then I can actually play the stream back and be able to listen to the audio that is associated with it. So I can also bring up my RTP streams here, and I can do an analysis on my RTP stream. I could also export this as an RTP dump, which would allow me to play it back using other tools that can handle RTP dumps. So this is a SIP call. This happens to be a sequence of SIP calls, but I can do the same thing with H.323 The one thing that I can't do here is if the RTP has been encrypted, and that's entirely possible. If you don't want people listening into your conversation, you would encrypt the audio. And if the audio is encrypted, there's really nothing I can do short of trying to get the keys from either end and then decrypting it, at which point maybe I could play it back. But that's really a complicated process, and it's not something that you're just going to be able to easily do. If you do happen to have RTP within your capture, then you do have a pretty good shot of being able to listen to the audio from your packet capture that went along with the voice over IP calls. Now, the user interface is great that we get with Wireshark, and it really makes for easy analysis. Sometimes, though, you need to drop down to the command line because maybe it's all you've got. So perhaps you are connected in via SSH and you really only have access to the command line. In that case, I can use Tshark. Tshark is the command line equivalent of Wireshark. It's similar to TCP dump or some of the other command line utilities like Snoop, for example. And all I've got to do is type Tshark, and I'm immediately capturing packets. And what is going on is it's just spitting out the information about the packet to the command line. It's not actually saving anything for me. I'm going to bring up the help now so we can see some of the things that we can do with Tshark. Now, the first thing that we can do is we can actually specify an interface. Now, the other thing that I want to potentially be able to do is actually want to save it. So I can say tshark -w and then saved.pcap. I'm going to change my snap length to grab the entire packet, and then I'm going to say -i en1, which is my Wi-Fi interface. Now what I'm getting is a number of the packets that are going by. So 69 packets have been captured, 73, 74, 76, and so on. I'm not actually getting the details from the capture at this point because those are all being written out to the file. Once I am done capturing, all I need to do is type Control-C, and then I've got my saved.pcap. And you can see that we've got 32,000 bytes, more or less, in my saved PCAP file. Now that I've got that PCAP file, it's actually really easy to just open it in Wireshark, just as we had looked at previously, opening up PCAPs that were on disk. This is just the same as that. I've got a PCAP on my disk, and I can open it up in Wireshark and then do all of the really cool analysis stuff that Wireshark is so good at. And I don't have to worry about trying to read through that on the command line. Tshark is great for capturing when you really want to dig into the analysis. Wireshark is going to be your better bet. But as I said, certainly there are plenty of cases where you may actually be limited to the command line and you really need to do packet captures. Once you've got the capture, you can export it off anywhere you want and be able to do the analysis at your leisure on another system. Now, we've taken a look at how to do some captures on the command line. What I want to do now is look at splitting capture files. What I've got here is a capture file that I have created using Tshark. So we've got saved.pcap, and if I take a look at it, I can get the size here. So this is a reasonably good sized PCAP. What I'm going to do here is I'm going to use a program called editcap. Now, I've got the help file or the help output here for editcap, and you can see that we've got a number of options. It takes an input file and an output file. And what I can do is I can use editcap to actually create a number of different files from one single input file. So I can use editcap in order to create files based on time, or I could just create it based on packets per file. So here I could do packets per file using -c, or I could use -i to say seconds per file. And so I'm just going to say edit cap, and then I'm going to say, let's say C is going to be 5,000, and then I'm going to give it the input file, and then I'm going to say split.pcap is going to be my output. So it should have actually created a number of output files for me with a number as well as a date stamp. So you can see that we've actually got the date there and we've got the time associated with it as well. So now I have created all of my split output files, and they're all 5,000 packets, but of course each packet is a different size, and so the output varies from one file to another simply because we are going on packets per file or frames per file. And since each packet or frame is going to be a different size, we're going to get a number of different output sizes right here. So we've created a number of split PCAPs from a single PCAP, which may actually give us the ability to really isolate a particular point in time if that's what we needed to be able to do as we're looking. So you can also use edit PCAP in a number of different ways. You could remove duplicate packets. You could actually chop packet sizes or lengths rather. Here you've got the chop length. You could ignore a number of bytes. So there are a number of things you can do with edit cap. It's a really powerful little tool to put in your tool chest as you're working with Wireshark, particularly if you're comfortable with the command line and want to be able to do some more advanced manipulation of the packet captures that you've got. So at this point, I've got a number of capture files that I have split into 5,000 packets per capture file. What I want to do now is I want to merge them back. And certainly I've got the original PCAP here. I could use that, but let's say that I don't. Somebody gave me a number of PCAP files, and I really just want to combine them into a single file so that I can open it up into Wireshark and then perform analysis on all of that. This would be really useful if you did something like used ring buffers, or you were doing some other sort of stop the capture at a particular point in time and then start up another file. Let's say you just wanted to merge everything into one because you discovered that your packet captures were of reasonable length so that you could merge them and not really overwhelm Wireshark or the memory that you've got. So you really want to put them all back together. So we're going to use a program called MergeCap, and we're going to look at the help for MergeCap. This is actually very simple. With MergeCap, I'm going to use -w and then my output file name, and then I need to give it a number of input files. I can also actually do some concatenation rather than merging. The merging looks at frame timestamps and then tries to interleave things if that's what they need to do. Concatenation just says take the first file and the second file and just append the second file to the first file. The third file gets appended and so forth from there. What we're going to do is we're actually going to merge. And so I'm going to say merge cap -w, and then I'm going to say new saved. I don't want to write over my original PCAP file. And then I'm going to do something like this. So what this is going to do is my command line here is going to expand that asterisk into all of the file names that match it. So everything up here is going to match that asterisk there because they all start with split and then they go from there. So what should happen is they should all go in the correct order. Not that it matters because we're merging, but just because of the way that the command line works, it's going to go in ASCII order, and all of these are actually in ASCII order here. So I'm going to use just split asterisk, and of course, if you only had like 2 or 3 and you couldn't glob them in this way, you could type all of the file names and then just put one after the other on the command line here. Because I've got a number of them, I've got a dozen, it's just as easy to do this. Now, let's just take a look at what we've got here for new saved. And it ought to look an awful lot like saved.pcap. So if I do LA and get all of the file properties for saved.pcap, it's very similar, but of course we have done some merging of all of them, and that may have actually ended up dropping some of the packets that we had captured. So we've actually got a slightly different set of output here in our new saved as we have in our saved. Now you could do some differences between these two to figure out where we've actually either gained or lost data. And as I look at this more closely, it looks like we've gained a few bytes. Not a lot, but it does look like we've gained about 392, give or take. So there is a little bit of difference here, and we'd actually have to open the packet captures up in order to maybe figure out where those additional bytes came from. But you can certainly use merge cap in order to take a number of packet captures and either merge them or concatenate them, and then you've got one single file as opposed to multiple files that you would have to look at individually. One thing that you may want to do when you're doing packet captures is we may want to run T-Shark and just have it start capturing data. Now here I'm just capturing to the command line rather than writing it out to a file. But what I might want to do is I might want to, rather than sitting here and monitoring it, I might actually want to create a stop condition. And so I'm going to bring up the help here for T-Shark, and we can look at the capture stop conditions right here. So I could capture after a packet count. So I've got a stop after some number of packets, n. So I could say T-Shark minus C, let's say 50,000, for example. And after 50,000 packets, it would just stop. I could also use a duration or a file size, and I could just stop the packet capture after we got some number of kilobytes. So I'm going to run T-Shark, and I'm going to say minus C, and let's just say 500. And so what I ought to get is 500 bytes, and then it should stop. And I'm just going to generate some traffic here in another window just to speed this up a little bit. Although there is data that's passing across my network, and I could get the 500 without helping it along, but it would take a little bit longer. So what I've got here are 500 packets that were captured, and then it just automatically stopped. So let's take a look again at some of the other conditions that we've got, because we've got duration as well as size. So let's just take a look at the duration just for fun. So minus A, and then we could say after some number of seconds. So I'm going to say T-Shark minus A duration, and I'm just going to say 15 here. So we're going to run for about 15 seconds, and then it should just stop after that 15 seconds and not capture any more packets. And that looks a little bit longer than 15 seconds, but we did actually get a stop there. So we got 225 packets captured in the amount of time that it allowed the packets to continue to capture here. Now, the other thing that we've got the ability to do here is we could actually do a ring buffer along the lines of what we were talking about with Wireshark. We can use T-Shark to do a ring buffer, and then we could actually do some capture stops in addition there. So we could do ring buffer duration and then number of files. So after some number of files, we could replace and use a ring buffer. But we could create a number of files using T-Shark here as well. And then, of course, we've got the capture stop conditions as we've talked about, either packet count or duration, file size, or the number of files that we have created. So T-Shark can be used to just do packet captures, and we can also automate it a little bit and have it just automatically stop for us, which is something that isn't as easy to do in Wireshark. It's another good reason to use the command line, because we've got some additional capabilities here that we can pass into this T-Shark program, still do our packet captures, still do the analysis in Wireshark, but we actually have some other things that we can do inside of T-Shark while it's running. We're going to go back to using T-Shark again to do some packet captures. And this time I'm going to limit what I'm capturing. I'm going to do that using capture filters. So we're going to look at the T-Shark help again. And let me scroll back up to find the section here that I'm looking for. So I've got -F and my capture filter. The capture filter is similar to the display and capture filters that we were looking at in Wireshark. We're going to create a little expression that we're going to pass into T-Shark so that it can determine exactly what it is we want to capture. And actually, before I do that, what I want to do is get my IP address here. So I'm going to just extract my IP address, and I'm going to just capture anything that includes that IP address. So T-Shark -F, and I'm going to say host, and that's going to be my IP address. This is only going to capture traffic that includes either messages to this system or from this system. So we're not going to capture anything other than that. So I'm only going to see messages that either have my IP address in the source or the destination. I'm not going to see any of the broadcast messages. I'm not going to see a lot of the other low-level details here. I'm only going to see messages that specifically relate to my system here. So that's a very simple capture filter. And I can also do things like ports. So I could say T-Shark, and again, -F, and I'm going to say port 80. This is either going to give me a source port of 80 or a destination port of 80. It's really not going to particularly care which direction that we're going here. As long as there's an 80 in one of the port messages, we're actually going to get that. I'm going to generate some traffic here so that we can actually see the filter being used. So you can see that all of these messages have HTTP somewhere, either on the right-hand side of this little arrow or on the left-hand side, as we see right here. So again, you can use T-Shark and capture filters in order to limit what you're actually capturing. And so you can restrict what you're getting and maybe get more isolated traffic. And of course, you can use this in conjunction with some of the other things that we were doing. So like the auto stop, for example, the capture stop syntax would work with this. So you're only getting just the traffic that you're looking for, and then it would still stop after some period of time. What we've seen so far is when we run T-Shark, it's got a predefined output format. We've got the frame number, and then there's a timestamp that's relative to when we started. We've got IP addresses, either IPv4 or IPv6, but we can actually change that. I can export just what I am looking for in terms of information. So I could, again, let's use a capture filter here. Source port is going to be 80, and let's just say host is going to be 172.30.42.13, which is my address. So I can combine two of my capture filters here. And then what I need to do is I need to say T field. So I need to actually get the field information out of the capture, and then I can specify the fields that I want. So let's say the frame.number, and then export IP.source, and then we're going to export IP.destination. So now I'm doing a capture here, and let me actually go generate a little bit of traffic here. Need to find something that's not HTTPS because we're only looking at port 80. And now you can see what we've got are my list of addresses here. So these are all of the IP addresses that have sent me traffic, and you can see that there are a number of them. Now, this is really kind of not helpful necessarily to just have it on the command line like this. So now what I could do would be, let's just say ips.txt. So now I'm really not going to see anything. I'm just going to generate some data here. And all you're seeing now is the packet capture count going up. So my number of captures is increasing. And I'm just going to generate some more traffic here. And now I can kill this, and I can just take a look at what I've got in my ips.txt file. And sure enough, I've got the same thing that I had before, but now it's in a text file. And now I could actually do some manipulation with it. So what I could do would be to extract that second column perhaps, and then do some sorting on it and get rid of duplicates, and then do a little bit more manipulation maybe. So I could perhaps import this into Excel, for example, and do some manipulation there. If you're familiar with some of the command line tools, there are some cool things that we could do with that. But if you want to just get specific information out of your packet capture and just get very specific data, you can use this -t fields and then -e, and you can tell it exactly what data you are looking for based on these variables that T-Shark knows about. So IP.source is one, IP.dst is another, and so on. You've got the ability to really kind of create your own packet capture based on these filters, and also the ability to just define the output format with the fields that T-Shark knows about. You may recall when we were looking at Wireshark, we had the ability to get a lot of statistics from the packet capture that we were getting. So I can also do the same thing using T-Shark here. And I'm going to go to T-Shark help. And first of all, I need to do -q. I don't necessarily want to see all of the packets that are being captured as we would normally see if all I'm looking for is statistics. If I'm looking for statistics, I need the -z. So let's just take a look here, and I'm going to generate an error here deliberately so that we can get a list of what we can look at. So I fed in one that I knew wasn't going to work. So that's the -qzio. Again, the Q is for quiet, Z is for statistics. And then I knew IO wasn't going to work, and that would allow me to actually get the list of types of statistics that we could actually get. What I really want to do is I want to look at the protocol hierarchy statistics that we had looked for before. And that's the IO, PHS here. So what I can do is just add the PHS there. And now we've got no output here, but I can assure you it's still gathering data. And I'm going to just generate some traffic here in a different window. And then once I stop the capture, what we'll get are the protocol hierarchy statistics. Looks very similar to what we had, other than this is text-based, and the other thing was a window within Wireshark that provided us basically the same thing. We've got all of the data, we've got the protocols, they're broken down into what looks sort of like a tree-like structure, because we've got indentation going on. So the top level is Ethernet, and then we've got IPv6 underneath that, UDP underneath that, and so forth. Now, I can also do some additional things, like, for example, I wanted to get the list of active hosts. So I could say hosts, and I'm doing my capture again, and I'm just going to generate a little bit more traffic here. And what I should get at the end is just a list of all of the hosts that T-Shark has seen communicating coming across my network interface. And I'm just going to type Control-C again. And I've got all of my addresses here. Now I've got a list of not only the IP addresses, but I've got the names that are associated with them. So it did the lookup for me as well. So you can see, again, I'm going to go back to the error so you can get a list of the different types of statistics that you can look at. So for example, we've got server message block, we've got SIP statistics that we had talked about with voice over IP, we've got remote procedure call statistics, radius, and a lot of other statistics that are available. So here's some for HTTP, for example, which you may want to look at as well. So there are a lot of statistics that are available in T-Shark. Again, this is something else you can do if you are looking at just having to use a command line and you're really looking for some of the statistics views. You can use T-Shark with -z and then provide the statistics that you're looking for. the text-based data is actually really good because you can import them into Excel or some other similar type of software and do manipulations on them and actually maybe do some detailed analysis on that level of data from these statistics. Well, we've covered a lot of ground here, and I want to talk a little bit about what we've actually covered, just as a little bit of a refresher. Now, we started with the welcome window here, and we looked over the different ways of doing captures. So we could do capture filters. We can just select an interface and go. We could also open up existing files from packet captures that we have saved, either using the command line or by doing a capture just inside Wireshark. We also looked at ways that we could do display filters. So for example, just looking at TCP packets, we could look at HTTP. We also looked through the various statistics that are available. So conversations, as an example. We also looked at endpoints. So we used the endpoints window also to look at GeoIP information, where the packet originated from based on the IP address. We've got some in Ashburn, Virginia, and Cambridge, Massachusetts as examples. We looked at different ways of sorting the data that we've got here in our packet captures so we can click on columns. We also looked at expert information that gives us a view of errors and warnings that Wireshark has located based on the packet capture, not necessarily something that's in the message itself, but based on analysis that Wireshark has done. And it looks at what it expects to see from a particular conversation and then determines whether there is something to be particularly concerned about based on what it has seen. We have looked at a number of other things that we can do with Wireshark. So, for example, the I/O graph. There's also the telephony menu. If you've got voice over IP calls, we can look for those voice over IP calls. In this particular capture, there aren't any. We can play back voice over IP calls. We can do analysis on those voice over IP calls. And we looked at ways that we could add the databases for GeoIP that we were talking about before. We looked at name resolution, turning on name resolution to resolve these IP addresses into names for us so that we can very easily determine what it is we are looking for. So if I go up to the view menu and then go to name resolution, I could add network resolution and have it do DNS lookups on the IP addresses. So I've actually got host names in my source and destination columns rather than just IP addresses that may not mean quite as much to me. So Wireshark is a very capable piece of software when it comes to packet capture and analysis. And we've really started to look at the various capabilities for it. Certainly, you will be looking for additional capabilities as you really start digging into Wireshark and how you could make use of it in ways that will benefit you and the jobs that you are trying to accomplish using Wireshark. Next step. So what can you do? If you go to wireshark.org, you can download the very latest and greatest Wireshark software. Once you've got Wireshark, of course, you can capture packets on your network, but you may want to take a look at different types of protocols that are available. And you may not have ways of capturing particular types of messages or protocols. So one thing that you can do is look at the Wireshark wiki and the sample captures. And using those, we can actually grab different protocols that you may not have direct access to. For example, spanning tree protocol. If you don't have a switched network where you've got multiple switches, you may not ever see the spanning tree protocol. You may not see the stream control transmission protocol, for example. If you don't have voice over IP, you won't see H.323 or SIP. So I could go looking for the SIP messages, and now I've got a number of packet captures that have been captured using SIP and RTP. A little bit lower, we've got H.223. And you can see all of the other protocols that there are captures for. Now, the other place that you can go is a place called pcapper.net. Most commonly, you're going to find packet captures of messages that may be a little bit broken. So if I look for SIP here, for example, what I'm going to get are some denial of service attacks along with a SIP register. So I could look at a DOS attack, and then a little bit later on, we've got a SIP torture attack here. So there are 24 bytes in this particular one. This is PCapper, and it's really associated with a product that does fuzzing attacks or malformed packet attacks. But they're still good packet captures that you can do some analysis with and really see some of the capabilities of Wireshark if you download some of these PCAPs. So certainly get your hands on a copy of Wireshark and then grab yourself some PCAPs in addition to just looking at what's going on your own network. Well, we've come to a parting of the ways, you and I really want to thank you for coming, and I hope you learned a lot about Wireshark along the way, and I hope that you've gone out and gotten yourself a copy of Wireshark and you're playing around with packets at this point and really getting your hands dirty, and I really hope that you have taken away a deeper understanding of networking in addition to Wireshark and the various things that you can do with it. So thanks again for coming. I really appreciate the time that we have spent together, and I hope you've learned a lot from it.